Ontem ninguém se
Oscar, já está a aqui? É só entrar na Zoom. André, sim. Ok. Conexão. Jorge, está ok? Não sei. Vamos ligar. Eu preciso de fazer a não, já está. Não sei. Ah, ok. Quer colocar assim? É isto? É sim. É. Tá bom? Mais alguma coisa? Não. Ok. Se precisarem disso.
Halo, probando dos, dos. Halo, probando dos, dos. Halo, probando dos, dos. Hello, probando. Dos, dos. Dos, dos, probando, probando, probando. Dos, dos. Probando, 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 probando. Dos, dos, prueba, prueba. ¿Sí? Dos, dos, dos.
Okay, great. So Jorge, are all speakers here? Hello? Anyone? Interesting.
Hello.
Hi, hi.
Actually, the speakers are not here yet. Oh, perhaps they are going to, right now I'm going to let them access the room.
Great. I somehow hear a huge delay on my side, but is everything okay?
Yeah, there are 20 seconds delay, but it's normal, don't worry.
Okay, sure, thank you.
现在是你的问题。
哦，可以了。哦，他们都有虚拟背景。
So Tian is here, and Tian Yue is here as well.
Yeah.
Oh, Tian, Yuda. Is Yuda here? Not yet. Okay, so we just missed the speaker 3 for this session. Okay, so in the meantime, all speakers, please do note that you have 16 minutes for the presentation and 4 minutes for the Q&A. So try to make sure, your turn is budgeted well. Otherwise, we have to, go huge delay or, overrun time. Okay, let me see. Do you guys want to have a dry run to see whether, the screen sharing is working on your side? Like Tian, Hao Tian, and
Oh, okay. Could you hear me?
Yeah, I can hear you.
Okay. I share my slides. Okay, sure. But I can share because someone is sharing.
Okay, maybe the technician is doing something there, then later. But at least I see the speaker on your side works well. And cool. Okay. Still, let me chase Yuda.
Okay. Then I share it. Oh, no. Hi. Wait. Oh. Me.
Okay, Jorge, can you hear me? No, you can hear. I'm not actually asking the.
I have
Yeah.
some problem. I can share my slides.
So you have technical problem, technical issue of the slide sharing.
Technical problem. Wait,
Right.
I have some technical problem. Okay. Just a moment.
But anyway, I guess we are wait 5 minutes to start. So take your time, Tina.
Oh, 怎么办？
So in the meantime, let me have a look. Who is the second speaker in the session? Tianyue, in case Tianyue comes off the technical issue in time, would you like to be the first speaker in this session?
Yes, of course.
Okay, let's just give Tianyue 1 more minute and see whether we should change the order. Okay, Yuda is here as well. Yuda, just in case you haven't, heard the instructions I just said, you have 16 minutes for presentation and 4 minutes for Q&A. So please try to budget your time well, so that we won't go over time for the session. Okay, Yuda?
Yeah, okay. Yeah, thank you.
Fantastic. So Tian, how about this? Tian, would you like to change the order to be the second speaker for the session? And we can let Tianyue be the first one, so that we can have maybe another 15 minutes or 20 minutes for solving the technical issues on our side. Okay, Tianyue, can you hear me, Tianyue?
Yeah, of course. Should I be
Right.
the first one?
Yeah, Tian, can you confirm? Otherwise, I'll just take it as a signal.
I have some. I also some issues to deal. And
So Tian, how about this? We let Tianyue or even Hao Tian, be the first 2 speakers. Then you can have some time to solve the technical issues on our side. Take your time, no problem. Now it happens for remote meeting. Okay, Tian. Okay, so Tianyue, please share your screen, and I'll make you as the first speaker.
Okay.
Right. So welcome everyone. Welcome to the first session of day 2 at SenSys. So in this session, we have 4 great papers lined up, researching the RF sensing for better human sensing. Okay, it's a very tiny topic, and currently, a very hot topic for SenSys and the mobile community as well. So our first speaker is Tianyue Zheng. So Tianyue is currently a PhD student in computer science from Nanyang Technological University, Singapore. Prior to his PhD, he got the MNG degree from the University of Toronto and the bachelor degree from Harbin Institute of Technology. So his research interests lie in RF sensing and deep learning, and got multiple publications in top, mobile computing journals and conferences. Okay, without further ado, Tianyue, the stage is yours. Please take over.
Okay, thanks for the introduction, and I'm very glad to present this very exciting topic today. So it for the first time explains how we can monitor human respiration and the general body movements. And my name is Zheng Tianyue, and this work is done in collaboration with Chen Zhe, Zhang Shujie, Cai Chao, and Professor Luo Jun. So existing systems for respiration monitoring cannot deal with body movements. So for example, some RF systems just totally suspend the system if any motion is detected, while some acoustic sensing methods can be really susceptible to real-life acoustic interference. We also have another work called Movify that will be presented at MobiCon 2021, but that one aims to recover both respiration and heartbeat, and also incurs a higher computational complexity. So this work, Movify, aims to recover only respiration while maintaining a reasonable system complexity. So before introducing the system design, let us define the scope of body movements. So our concerned body movements should satisfy two conditions. The first is that the human subject should stay within the radar field of view, so the radar can see the human subject. The second condition is that the distance from the radar to the human subject should lie within a reasonable range and be around its mean. Therefore, the human subject cannot greatly change his position or posture. So there is no need to track the human subject. So let me first give you some basic theory of capturing human respiration with IR UWB radar. Suppose we have a radar and it sends out radio waves into the space which bounce off targets. And due to the large bandwidth of the radar, we can see that different objects in the space can be clearly differentiated. For example, in this figure, we can see a human subject and a wall are on different distances from the radar. However, a single frame of radar signal is not enough for respiration monitoring. So the radar sends out a series of signals at a regular interval and stacks the received signal on top of each other to form this signal matrix. And as circled in the red box, we can see some periodic movements, and that is respiration. Although we can see the respiration, how can we describe it quantitatively? One may think that we can simply use the amplitude or the phase of the signal, but neither of these two quantities can describe human respiration perfectly, and I will explain why. I'll give you two examples. In the first signal segment, we can see that the strength of the amplitude of the signal is time varying. And in the second signal segment, we can see that the phase of the signal faces some flipping and wrapping issues. So why can't we just use amplitude or phase of the signal? To understand why, we display the signal on the IQ diagram, which is the 2D representation of the signal. We can see that the received signal, which is the blue vector, is actually the sum of two other vectors. That is the green vector, which is known as the body background reflection offset. It is a DC offset. And also the red vector is called the respiration-induced variation. So as the human breathe, his chest moves back and forth. And the red vector rotates in the IQ space and traces out an elliptic arc. The reason it is elliptic is that the radar cross-section change as the human breathe. So now you may think that we can simply calculate the center of the ellipse and move it back to the origin. However, this is only the static case. What if the human subject is under movements? We can see that the ellipses are blended together and the signal is no longer analyzed, can no longer be analyzed by simple geometry. So to process the signal, previous methods cannot deal with IQ components simultaneously. So they fall back to the 1D signal processing methods. For example, in these slides, some people use bandpass filter while others use some mode decomposition algorithms. But we can see that the recovered waveforms lack some details. For example, the peaks and valleys of the waveform. And also the recovered respiratory rate can also be wrong. So these challenges require us to develop a system or algorithm to process the IQ bivariate signal, as well as being robust to noise and human movement. And in the next few slides, let me introduce the system design of Morify. So the first step is to locate respiration in the signal matrix. We use a CFAR algorithm, which is an adaptive algorithm to find peaks against its background. So here we find the largest variation matrix. We find the fast time index, and we obtain a submatrix around that fast time index to get this submatrix containing the respiratory signals. The next step is data augmentation. We do this for two reasons. The first one is data collection is very difficult because we have to coordinate between the human subject and the various data recording devices. The second reason is that there is an intrinsic relationship between the IQ components of the signal. And by doing this, we hope that we can help the network or the algorithm to understand the relationship. So to solve these problems, we propose IQ-VED, in-phase quadrature variational encoder-decoder. So the network is actually inspired by the idea called variational inference. The inference here means that we try to discover the underlying variables that's generating human respiration, body movements, as well as interference. And variational means we do this in an optimization approach. And as you guys all know, the most popular way nowadays to do optimization is gradient descent by backpropagation, which is enabled by the deep learning neural network. And we can see that the network is an encoder-decoder architecture. The two encoders encode the IQ signals separately and align them on the latent space. We hope that the decoder can selectively choose some useful representations on the latent space and decodes the respirations waveform. To implement IQ-VED, we employ the following loss functions. The first loss function is the reconstruction loss, because we try to minimize the difference between the recovered respiration waveform and the ground truth. The second loss function is the IQ regularizing loss. So instead of letting the encoders return discrete vectors, we force the encoder to give us probability distributions because we want the network not to overfit on training data, but to be able to generalize to unseen data during training. The third loss function is called the distribution alignment loss, because the IQ signal shares some common structures, and we want to align them in the latent space. And it is implemented by the two Wasserstein distance. The final IQ-VED loss is a weighted sum of the three respective loss functions. Okay, next we come to the evaluation part. First, let me give you the intuitive waveform result. For example, in the typewriting case, in the raw RF signal, we can see that the signal, the movement is sporadic. It has some intensive periods and also some non-intensive ones. Fortunately, IQ-VED can recover not only the waveforms during the intensive periods, but also the non-intensive ones by correcting the phase of the signal. Next, we look at the overall performance of Modify. We are most interested in the cosine similarity between the recovered waveform and the ground truth. We can see that the playing on phone and the shaking legs has the least impact on the recovery performance because they only involve movements of the arms and legs and not related to the human chest, while walking on a treadmill and standing up, sitting down has the most impact on the recovery performance because they all involve very large movements. Next, we compare Modify with a baseline method called breath listener. It is chosen because it claims to be robust to movements of running vehicles in driving environments. For example, in the turning over in bed example, we can see that while Modify recover almost perfect waveforms, breath listener only recover very coarse-grained ones. And as the movement grows stronger, we can see that breath listener cannot even give some meaningful result. And we can also see that Modify outperforms breath listener in almost all benchmarks. At last, we studied the impact of practical factors. For example, for the training set size, as the size grows, we can see that the performance grows gradually and then saturate. In practice, we choose a training set size of 8,000 because after that, the performance barely increases anymore. And we are also interested in the latent space dimension. If the dimension is too small, for example, 8, the expressiveness of the network is limited. So the performance is not very good. On the other hand, if the dimension is very large, the network becomes very difficult to train. So we try to strike a balance between expressiveness and compactness of the network. And we use a latent space dimension of 64. Modify can be potentially used for various medical applications. However, we didn't claim that Modify can be used for disease diagnosis because we only have healthy human subjects in our experiment. But we think in the future, researchers and medical professionals can help evaluate the performance of Modify in recovery, in diagnosing pulmonary diseases. And thank you for watching this presentation. And questions?
Okay, great talk. Let's see whether we have some questions from the on-site audience. Just wait for.
Hi there, Andrew Markham, University of Oxford. Thank you very much. Great presentation. I would just like to know, did you consider using complex valued neural networks instead of decomposing the I and Q into two real valued separate streams?
Yeah, we did try to use complex networks, but on one hand, the theory for complex networks are not very mature yet. And on the other hand, we find that using complex networks, they are very difficult to converge. Therefore, we choose to to treat the IQ components separately.
Great. Okay. Thank you.
Okay. And there's a question from Slack, but let me just double check if we have more questions from the on-site audience. Okay, if not, so there's a question asked on Slack. So can you describe the CFAR algorithm in more detail in your work? Yeah.
Yes. So it is basically an adaptive algorithm to detect peaks because if you simply detect the max values in the signal matrix, there may be some background reflections that is also very strong. So we use an adaptive algorithm to detect peaks against its background. So if the background is very strong. We require the signal to be even stronger to identify the human subject.
Okay, good. Okay, any more questions from the online audience? If not, actually, I can weigh in one. So in your case, you separately treat the eye signal and the Q signal, right? But essentially, they actually occur in pair when collected. So they have some temporal correlation among them. So do you think your separate treatment into network branches will somehow bridge such kind of already well-defined temporal correlation among them in modeling?
Yes, because we actually we align them intentionally by aligning them in the latent space using the distribution alignment loss, which is enabled by the 2 Wasserstein distance.
Okay, so you mean the temporal correlation are somehow preserved?
The temporal correlation is preserved. Yes.
Okay, cool. Right, I see still there are somewhat. Okay, last question. Did you try using 2D convolution? Your inputs look good for image-based processing. That is asked by online audience on Slack.
Yeah, of course we tried 2D convolution, but we think in nature the IQ signal is a time series signal. So we think 1D convolution is the right way to go.
Okay, great. So I guess due to the time limit, we'll have to let I'll tend to answer more questions offline. And let's move to the second speaker. In this case, Tiantian, is a technical issue solved on your side?
Yes, I can the Tianyuan should close his sharing.
Okay.
I can over my sharing.
Great.
Thank you. Okay.
Awesome. This screen. Okay. So let's welcome the second speaker, actually the first paper in the session. Okay, so
Yeah.
Tiantian is currently working towards his PhD degree at the Zhejiang University, following her undergraduate study from the same university. Her research interest broadly lies in wireless sensing and cyber-physical security. So Tiantian, the screen is yours. Please get started.
Hello, everyone. I'm Tiantian Liu from Zhejiang University. I'm glad to introduce our work. We was a noise-resistant multimodal speech recognition system using millimeter wave and audio signals. This is a joint work conducted by Zhejiang University and the State University of New York, Buffalo. Voice user interface plays an important role in intelligent things, such as smart healthcare, smart home, and intelligent driving. The speech recognition applications entitle voice user interface to the capacity of accurate comprehensions on users' intentions. With the automatic speech recognition, commercial voice user interface products have gained popularity in many fields over the recent years. However, how about automatic speech recognition in complicated conditions? Let's watch the video.
Remember, Tannenberg at 9:30.
Fire off.
Fire off.
Open door.
Repeat that.
Hey, open door.
Play on the floor.
Open door.
Whether the technology is really convenient or embarrassing, the traditional speech recognition system only use microphones to record audio in air, bringing about 2 major limitations: susceptible to noise and a limited distance. How to overcome these limitations? To address these limitations, researchers proposed several methods. One of mainstream methods is based on microphone-based methods, including microphone areas or deep neural networks. Such audio-based methods always exploit microphone areas or deep neural networks to perform speech enhancement. However, These microphone-based methods require clean audio signals and are susceptible to unpredictable noise. Besides, some research leverage cameras to capture the lip motion. Fusing the audio and visual information can improve the ability of speech recognition, but audio-vision methods are limited by face masks, lighting conditions. Another ultrasound-assisted method integrates the mouth motion captured by the ultrasound. The ultrasound-assisted speech enhancement technique is merely applied into condition scenes due to the short walking distance and the specific cultural requirements. Therefore, how do we solve these problems? Firstly, let's view how audio is produced. Voice production is a fluid structure acoustic interaction process. The airflow induced by the lung propagates through the vocal tract and collides the vocal fold. The human voice is the cause effect production when the airflow is modulated by the vocal fold acting. Here we leverage a millimeter wave radar to sense the vocal vibration owing to its low distance and the noise resistance advantages. It has been demonstrated that the millimeter wave signals contribute to voice information. Nevertheless, the millimeter wave signals are sensitive to the user motion. So, after comprehensively the merit and demerit of the microphones and the millimeter radars, we propose the multimodal speech recognition system based on the millimeter radar and the audio modalities. Here, the millimeter signals encourages the noise-resistant speech sensing in spite of face marks, while the audio signal collected by a microphone serves as a guide to collaborate features in the millimeter wave signal under motion, even under motion interference. To achieve the multimodal systems, we should know, firstly, what correlation exists between the millimeter wave and speech signals. What is the cause-effect production of the vocal fold vibration, while the millimeter wave signals are modulated by the vocal vibration when sensing? Both are derived from the vocal vibration. To realize the multimodal systems that combines millimeter wave and the audio signal for speech recognition, some problems need to be addressed. For example, how to fuse signals of different modalities. We designed a fusion network to fuse the millimeter wave and the speech to produce the fusion feature. And the fusion feature is fed into the semantic extraction to output the text. This is the structure of our fusion network. The fusion network comprises the residue blocks with ECA, reclamation module, and projection module for multimodal signals fusion. The reclamation module is embedded into the middle of the network, and the projection module is put at the end of the network. The reclamation module exchanges the valid features for the mutual reclamation and the characteristic enhancement. As shown in the right figure, the attention mechanism adaptively selects useful information in both millimeter wave and the speech modality. After interaction and collaboration, the speech supplies the acoustic information to the millimeter wave. Meanwhile, the millimeter wave provides the speech with the feature about vocal vibration. More specifically, if the speech suffers interference and attenuation, the meanwhile feature will guide the network to capture underlying representation. Lastly, the projection module projects the respective of different modality into a joint feature space and adjust the weight confusion dynamically. Traditional methods ignore the dynamic distribution of the weights across multimodal domain. Instead, they focused on all multimodal features equally. Inspire co-attention, we create another novel attention-based module to project a multimodal feature into a joint feature space. Projection module construct a similarity matrix of two modalities to mention the correlation between each element of voice and each element of millimetry. With the similarity matrix, we can respectively map each modality into another modality space. Eventually, the fusion result is fed into the semantic extraction. To identify the speech context, we choose listen, attend, and spell, a widely used end-to-end deep learning approach. Since its excellent performance on small-scale training data and does not rely on any assumption about the proper distribution of character sequence. Here we stack two PBLSTM layers as a listener, while the speller contains two LSTM layers and a softmax layer. With the aid of LAs, we will extract the semantic information from the joint features. However, in realistic scenarios, the user does not speak commands all the time. If our assistant is always fusing the millimetry and audios, it will cost too much energy. After addressing the fusion challenge, we need to solve the problem how to detect the voice activity in an effective and real-time manner. When the user's voice is overlapped by multiple noises, it is a challenge to detect voice activities only relying on the audio. Recalling the model of the millimetry and the speech signals, they share the identical frequency with the vocal fold displacement. If the phase of the millimetry signals and the voice share the component with the same or similar frequency, we will obtain an energy peak at the low frequency band of the coherent demodulation. Thus, we multiply them to yield the low frequency component. Based on it, we can detect the voice activity. We use the threshold method to detect the component, multiply the millimetry and the audio. Then we feed it into a low-pass filter and the threshold detection. When the spectral entropy of a component is larger than a given threshold, it indicates the voice activity occurs. Even if the noise rings audio or millimetry, or even worse both, the coherent demodulation still works. In our experiment, we can observe the low frequency component in frequency spectrum. We conduct the experiment to evaluate the effectiveness of our method. We collect 3-second millimetry signal and audio signal when people in silence or speech. In our experiment, we can observe that our approach outperforms the millimetry only and audio only methods with an accuracy 97.12%. In a multi-person scenario, surrounding audios and motion from ambient people will disturb the performance of the proposed system. Audio only automatic speech recognition highly distinguishes the target, while the millimetry only system highly distinguishes the target by its emotion. Thus, we choose the millimetry audio mechanism to leverage multiplication production to determine which signal comes from the target user. We successfully compare each low frequency component by multiplying millimetry signals with audio signals after voice activity detection. We extract the linear predicoding from the multiplication product, and then the LPC is fed into one class VN to judge whether wake-up words happen. LPCs can be quickly calculated with the limited time, but still preserve trees. Then we build the prototype of wavewords using the off-the-shelf millimeter radar and microphone. Our metrics are character error rate and word error rate. we compare the system with a state-of-the-art automatic speech recognition. We evaluate speech recognition performance of viewers under 4 different noise conditions: chatting, traffic, music, water flow. Viewers outperforms traditional systems by at least 20 times. Viewers achieve the character error rate within 1% and the average word error rate within 2.5%. We also conduct the comparison experiment and a large study. The comparison result shows that every module we proposed plays a vital role in speech recognition performance. We also conduct the experiment while the user located at different distance and orientations. The result reveals that the viewers suppose flexible and convenient speech recognition performance. The result is less than 1.5% in orientation when the distance is less than 9 meters. To investigate the effective of proposed target module, we further conducted the experiment in a multiple sensing. The system is highly effective against interference from people around. By average recognition result, we get an overall speech recognition accuracy of 1.2%. We also evaluate the robustness of viewers when user in a body motion. Motion interference has a limited impact on the performance of the system. The average character error rate are slightly high, but are mostly less than 1%. We also studied the generalization of viewers in a vehicle. The results demonstrate that our system is competent for speech recognition, regardless of the wobble of the memory radar. The average is always staying below 0.5%. In summary, we designed a multimodal automatic speech recognition system named Viewers for voice user interface public application. We refine the attention-based multimodal fusion network with the cross collaboration. The Viewers maintains a low error rate with 1% under unfavorable conditions, and its range reached up to 10 meters. Thank you for your listening. Any question?
Okay, on-site audience, any questions? Okay, if not, let's pick some questions from the online audience. So one question, actually I found it on YouTube. So consider wave signal and audio signal have different propagation speeds. How to synchronize both signals in your DNA model? That's a question asked by the YouTube audience.
I can't hear clearly. I beg your pardon.
So the question, how about now? Okay, the question is like the wave signal and the audio signal have different propagation speeds, right? How do you synchronize both signals in your DNA modeling?
Okay, but in our system we writing our coding to send the two modality signals simultaneously, and after we receiving the signals, we will segment the signals and perform the interpretation on the millimetry signal to align the speech signals. Okay.
Okay.
Yeah.
Not sure. Xu, if you have further questions about it, you can keep asking. In the meantime, let's have a look about second question. So can you elaborate how you locate the targeted user in multi-user case with mmWave? Do you use beamforming to help the user targeting?
Okay, let's in a multi-person scene, the millimeter radar will receive multiple signals. Firstly, we use CFAR to detect the multiple objects. Then we successfully to multiply the millimeter signals with audio signals, and successfully to require the multiplication production, and then we feed into our we first extract the LPC code, LPC features, and feed into one class SVN to determine whether there is a wake-up word. Our wake-up word is defined as like keywords. Then we can find the targeted user. That is the targeted signals. Yes, from the targeted beam in our spectrum after CFAR. Yes. Okay. That's all.
Okay, thanks. Due to time limits, we have to move to the next presentation. So thank you again, Tiantian, for the talk, and please answer the questions offline on Slack. Okay. All right. Let's move to the third paper in this session. Haotian, could you try to share a screen?
Okay.
All right. So in the meantime, I can introduce Haotian. Haotian is currently a postgraduate student at Tsinghua University. His research interests include wireless network coexistence and wireless sensing. So Haotian, please go ahead. But I guess the screen sharing, we can see the notes as well.
Okay.
If you are fine with that, we can go ahead. But yeah, up to you.
Wait a minute. Does it work now?
Yeah. Please get started.
Okay. Thanks for the introduction, and hello everyone. This is Haotian Jiang from Tsinghua University. Today I'm presenting SenseMe on the right, accurate mobile sensing over a LoRa backscatter channel. My collaborators are Jiacheng Zhang, Xiuzhen Guo, and my advisor Yuan He. Wireless sensing is a key enabling technology for ubiquitous Internet of Things applications. In the past decade, we have witnessed a large body of studies on wireless sensing. The wireless technologies for sensing range from acoustic, RFID, and Wi-Fi to LoRa and millimeter wave. The sensing capabilities extensively cover motion and activity sensing, mobility measurement, environmental sensing, and material sensing. However, there is still a missing piece in the conception of ubiquitous wireless sensing. That is how to sense the condition of a mobile target, especially at a long range. Our work in this paper creates a new sensing technology for cyclists in the public bicycle sharing system. Many of such bicycles are equipped with a long-range communication module, such as LoRa, so that their location data can be uploaded. This communication module can act as the signal sources for wireless sensing. As a key technology of low-power wide area network, LoRa extends the communication range to several kilometers via CSS modulation. Previous studies have utilized LoRa signal to extend the range of wireless sensing to tens of meters. However, as the sensing range increases, there are more moving targets that fall inside the sensing range and therefore submerge the signal reflection of the target of interest. How to distinguish the target of interest from other moving targets in the environment has become an urgent challenge. Some previous works leverage beamforming to mark the area where the target is located, but at the same time, it limits the ability to sense moving targets. Therefore, these existing works cannot perform sensing on mobile targets. The technology we invent, namely Palantir, utilizes the LoRa communication as the excitation carrier and attaches a simple backscatter tag for cyclist sensing. Our proposal is attractive owing to multiple advantages. First, Palantir does not occupy the communication channel of LoRa or backscatter, but senses the cyclist on the set channel instead. Palantir extends the sensing range to 100 meters and performs long-range sensing with a battery-free tag. Moreover, Palantir is extremely robust against the influence of mobility, and hence can sense the condition of mobile targets for the first time. At a high level, the basis of Palantir's sensing is that the OK modulated signal can be divided into two states of on and off in the time domain. These time domain signals can be stabilized by removing the modulation of CSS and then manifest two clusters in the IQ domain. The signal in the off state is utilized as a reference in the sensing model to sense the movement of the target, and we will explain this model further. Theoretically, to perform sensing with LoRa backscatter, we firstly need to remove the CSS modulation of LoRa on the baseband. A conjugate multiplication, as described in this figure, explains how to perform signal stabilization in theory. Then we can perform sensing with the stabilized signal. The signal in the off state does not contain the backscatter signal, while the on state is a composite of the LoRa signal and the backscatter signal. The stabilized signal will manifest two clusters in the IQ domain, representing the on and off states respectively. This means that the target of interest is uniquely marked via the switch of on and off states in the time domain, and we can derive the backscatter signal by a subtraction of clusters in the IQ coordinate system. Since the movement of backscatter tag changes the propagation distance of signal, the backscatter signal in IQ domain rotates with the move of the tag. Hence, we can sense the movement of the tag by calculating the rotation angle of the backscatter signal. However, it is non-trivial to complete the sensing task in reality because sensing sets higher requirements on channel quality than communication. Many redundancy introduced for the robustness of communication does not benefit sensing tasks. Specifically, we separate four types of challenges that are coupled with each other, and they must be solved to perform accurate sensing. Firstly, although LoRa does not modulate the data in amplitude, the amplitude of the LoRa signal sent by the commercial device manifests a visible instability in the micro-benchmark experiment. This amplitude instability may submerge the state change of the backscatter signal and hence results in an inseparable cluster. Secondly, carrier frequency offset, sample time offset, and clock drift are widely present in every transmitter-receiver pair. This offset and drift distort the phase of the received signal, and the existing composition methods designed for communication cannot be applied to sensing tasks. As a result, the on and off state will manifest concentric circles instead of clusters, which significantly reduce the accuracy of sensing. To make matters worse, due to the large number of frequency hopping in CSS modulation, spectrum leakage is very common in LoRa signals. The spectrum leakage will couple with the aforementioned offsets and drifts, so that the original continuous signal is divided into discrete segments. Finally, we find that the clusters of the received signal are arc-shaped, which means that the signal suffers from multiplicative noise. And the result of multiplicative noise is a disturbance to the clustering algorithm in IQ domain. In order to solve these four types of challenges, we designed the system of Palantir. The overall design includes four modules, namely LoRa preprocessing, signal shaping, clustering, and sensing. In the first module, Palantir calculates the starting time and frequency of each LoRa chirp. Next, Palantir shapes the amplitude and the phase of the received signal, respectively. The amplitude shaping part is used to remove the low-frequency amplitude envelope through a filtering algorithm while retaining the on-off state transition. For the signal phase, the baseband waveform is removed by conjugate multiplication. The offset and drift are modeled mathematically and then compensated by curve weighting. The signal after shaping will be stable in the time domain so that it can be clustered. In order to deal with multiplicative noise, Palantir performs clustering in the logarithm of the amplitude space coordinate system. This is because the multiplicative noise in IQ domain appears to be additive in the logarithm of the amplitude phase domain. Although the cluster of off-state acts as a reference and is expected to be static, it manifests a phase difference between adjacent sensing windows due to the joint influence of sample time offset and spectrum leakage. Fortunately, we can reasonably assume that the tag movement between the adjacent sensing units is small. So Palantir can align the cluster centers and ensure the consistency of the judgment of clusters on-off state to avoid ambiguity. Finally, Palantir gets the backscatter signal in IQ domain and senses the movement of the target by tracking the change of the signal. With the complete system design, we build a prototype and conduct experiments to study the performance of Palantir in various state situations. We take a commercial LoRa node as our transmitter and a USRP as the receiver. Both the transmitter and the receiver are equipped with an omnidirectional antenna. The LoRa node runs at 902 MHz with a spreading factor of 11 and a bandwidth of 500 kHz. A WISP is used as the backscatter tag, and the reciprocating machine is used to generate a controllable periodic motion in the benchmark experiment, and it is baked on a trolley. The USRP is placed at a fixed position on a road and samples at 1 MHz. We change the position of the transmitter and backscatter on the outdoor asphalt road and move them with a trolley to simulate a mobile scenario. Palantir senses the motion period and motion amplitude of the tag to determine how fast and how deep to break it, respectively. We rely on the deviation of the sensed period and amplitude to evaluate the performance of Palantir. We first conduct benchmark experiments to study the performance of Palantir under different TX-RX distance. The motion period deviation and motion amplitude deviation when the TX-RX distance is 10 meters have medians of 0.3% and 4.39% respectively. As the distance between the TX and RX widens, the sensing accuracy decreases due to the decrease of signal-noise ratio. Nevertheless, the median deviation of motion period remains as small as negative 0.2%. We further evaluate Palantir under different motion amplitudes and motion frequencies, and the results show that Palantir works well in various settings. To evaluate the robustness against the influence of other mobile targets, a volunteer is instructed to move in different speed. We also evaluate the performance of Palantir in mobile scenarios by moving the trolley at different speed. Finally, we conduct a case study about respiration sensing while riding a bicycle. We attach the omnidirectional antenna to the public bicycle. The backscatter is attached onto the clothes on the chest. The respiration of a volunteer is sensed at different distance. Then the volunteer is instructed to ride the bicycle at different speed. Here we show some of our results. The right dotted lines mark the respiratory period detected by Palantir. It is shown that Palantir obtains stable respiratory period, which can be used as a clue for respiration monitoring. So to sum up, in this work, we present Palantir, a first of its kind long-range sensing system based on the LoRa backscatter. Palantir extends the sensing range to 100 meters and can be applied to both stationary and mobile targets. To achieve this, we separate the coupled challenges and design a complete signal processing scheme. Although we design Palantir based on the LoRa backscatter, our work fills the gap between sensing and communication that commonly exists in all kinds of wireless signals. We evaluate the performance of Palantir by performing comprehensive benchmark experiments, and we also build a prototype and conduct a case study of respiration monitoring in the real world. This will conclude my talk. Thank you for your time, and the questions are welcome.
Okay, great. Thanks for the talk. Any questions from the on-site audience? Please speak up.
Great. Thank you very much for the talk. Very, very interesting. What's the maximum distance, separation distance you can have between the LoRa transmitter and your backscatter tag?
So the transmitter and the backscatter tag should be within several meters. And this is because the signal attenuation after the reflection commonly exists.
Okay, thank you.
Okay, any more questions from the on-site audience? If not, let's have a look about the online audience. Okay, we've got a question from Jing. How did you obtain the ground truths for the motion amplitude? If you use a wearable device, it seems to me that even the difference between sensing modalities should cause large differences in results.
So in the macro benchmark, benchmark experiments, the ground truth is obtained by control the reciprocating machine, and we exactly know the ground truth, and the case study we just try to evaluate the feasibility of sensing in reality. So the ground truth of case study is not obtained.
So personally, I have a question about the evaluation metrics. So any implication or rationale when you choose this, evaluation metrics against, let's say, why don't you just measure the heart rate of some, cyclist, since you are doing the, measurement of respiration anyway.
Right.
I mean, the evaluation metrics you chose for this work is based on what kind of a rationale? What kind of a use cases it could enable?
So in fact, we think the public bicycle company can get the anonymous information of the cyclists, the respiration of cyclists, so that they can provide emergency assistance or just improve their bicycle design and something like that. So, and respiration sensing is just it's just a good choice to evaluate the condition of the cyclist.
Cool. Okay, maybe for some health monitoring, right? Okay. All right, thank you. Please have a look about the Slack. In case there are some questions, you can answer offline. Okay.
Okay.
Thanks, Haotian. Let's move to the last paper in the session. So Yuda, could you try to share your screen? And in the meantime, I'll try to introduce Rita. So Yuda Feng is a third-year PhD student at UMass, supervised by Jie Xiong and Deepak Ganathan. His research interest lies in building novel wireless sensing systems for mobile health and human-computer interaction. So more recently, he is researching innovative methods and systems for LTE-based sensing. So Yuda, the screen is yours.
Yeah, thank you. Okay, let me start now. Hello, everyone. My name is Yuda Feng. I'm from the University of Massachusetts Amherst. Today, I will introduce our paper, LTE-based pervasive sensing across indoor and outdoor. When we are using a public touching screen, there would be a lot of virus, which can be a big problem in the COVID pandemic. So people would prefer contact-free approaches, such as gesture controlling. For healthcare, the traditional sensor-based approaches are usually uncomfortable because people have to wear a lot of devices. On the contrary, RF sensing-based approaches are usually imperceptible and will not affect people's normal life. Because of the contact-free nature, RF sensing has become a popular research area with a lot of applications enabled, such as gait recognition, gesture controlling, and even fine-grained respiration monitoring. Various technologies are proposed in RF sensing. Among them, Wi-Fi is the most popular one because of the wide deployment of Wi-Fi access points. But pervasive Wi-Fi coverage is only limited in indoor environments. And even though Wi-Fi communication is pervasive in indoor environments, Wi-Fi sensing is not. The reason is a huge gap between Wi-Fi communication range and Wi-Fi sensing range. So why Wi-Fi sensing range is much shorter than Wi-Fi communication range? There are several reasons. First, the Wi-Fi communication uses a direct signal from the transmitter to receiver. And the Wi-Fi sensing uses a reflected signal from the human body, which contains only a small portion of energy. And Wi-Fi communication uses one-way transmission, while Wi-Fi sensing uses round-way transmission. So we conclude that Wi-Fi sensing has a limited coverage even in indoor environments. Wi-Fi sensing also has other drawbacks, such as affecting Wi-Fi communication and blind spot orientation issues. In normal Wi-Fi communication, there are several types of packets, such as Wi-Fi beacons and data packets. Wi-Fi beacons can be used for sensing. They are equally spaced in time domain, but the low packet rate limits the capability of Wi-Fi beacons in a lot of applications. And data packets have higher packet rate, but they are affected by the arbitrary interval problem and the packet loss. So these two are both not preferred in Wi-Fi sensing. In previous Wi-Fi sensing works, people use dedicated packets for sensing. They would occupy the channel and affect the normal Wi-Fi communication. For blind spot issue, when the target moves a small distance, the performance can vary a lot, from good to bad to good to bad, or to say the blind spots. So we conclude that blind spots occur frequently in Wi-Fi sensing. It is similar for the orientation issue, when the target is facing different orientations. The performance can vary a lot. For example, in the figure, a person is breathing. The front side has the largest displacement, and the left and right side have the smallest displacement. So when we are doing Wi-Fi respiration sensing, our performance can vary from good to bad to fair to bad to good. Or to say, the orientation of the target affects the performance a lot. Here comes to the question, can we achieve truly pervasive sensing? The answer is yes. In this paper, we propose to include LTE-based sensing into the ecosystem of RF sensing. There are several unique advantages for LTE sensing. In the following slides, I will introduce them one by one. The first is the pervasive coverage of LTE sensing in indoor and outdoor environments. And people can have free access to the reference signals which can be used for sensing. The reference signals are broadcasted 24 hours, 7 days. People can passively receive the reference signals without any data plan. Second, the grids of the reference signals are reserved in LTE protocols. So LTE sensing does not affect the data communication at all. Also, LTE signals are well organized without any gap in time domain. So it leads to uniform sampling, which is suitable for sensing. In comparison, there are usually collision avoidance schemes in other technologies, such as the CSM ACA for Wi-Fi and Aloha for LoRa. They are both affected by the arbitrary interval problem and packet loss. Another unique advantage for LTE sensing is a high frequency sampling of 1000 Hertz. In comparison, a normal Wi-Fi router can only support 50 to 250 Hertz. So the LTE sensing can enable high speed and high frequency movement detection. The last advantage is the frequency and spatial diversity of LTE base stations. LTE base stations have optimized placement to achieve maximum coverage. So there are usually multiple LTE base stations around the target. And each LTE base station transmits at a different frequency. So we can utilize the multiple frequencies to realize a combination gain. There are 15 base stations detected in our university. Although there are a lot of advantages, we still need to deal with several challenges before we can realize LTE sensing. In the following slides, I will introduce the main challenges and their corresponding solutions. The first challenge is a random phase offset between the LTE base station and LTE terminal. LTE base station and the terminal have different clock source. They are not synchronized. Due to the asynchronization between the transmitter and the receiver, there are several issues, including carrier frequency offset, sampling frequency offset, and even sampling timing offset. As a result, the phase of the received signal drifts at all directions, so we cannot use the phase information for sensing. The solution is a phase subtraction between two receiver antennas connected to the same clock source. As you can see here, receiver 1 and receiver 2 share the same clock source. So the phase offset at receiver 1 is equal to Z1 at the receiver 2, which means they are sharing the common phase offset. And we can remove the phase offset by subtraction. After phase subtraction, we can achieve much stabler phase information. In this figure, the phase is converged to about 25 degrees, which can be used for sensing after further signal processing. The second challenge is interference. Received signals can be divided into static passes and dynamic passes. Static passes are caused by the static environment, and the dynamic passes are caused by the target and other moving objects, such as swinging trains, cars, and pedestrians. We call them interference. On the other hand, LTE base stations are usually very far away from the target. So the LTE signals travel through a long propagation path affected by a lot of moving objects. So there are usually much more severe interference than other technologies. First, let me introduce the ideal case with only static path and a target. Here, the blue arrow represents the static path, and the yellow arrow represents the dynamic path caused by the target. When the target is doing some periodic movement, the target path is also changing periodically. Next, we consider the composite vector. When the target is moving periodically, the composite vector is also changing periodically. Now let's look at the phase variation of the composite vector along time. At the initial point, as you can see here, the phase of the composite vector is theta. And when the target is moving periodically, the phase of the composite vector is changing from theta to 0 to minus theta to 0 to theta. It forms a periodic pattern along time, which matches the periodic movement of the target. Based on the above observations, we can get some conclusions. First, the periodic movement causes an arc in the IQ plane, and the periodic movement causes a phase variation of delta phi. By repeating such phase variation along time, it forms a periodic pattern which matches the periodic movement of the target. So we can get our key intuition of our solution. Here in coordinate C1, the green arc represents a target, and it causes a phase variation of delta phi 1. And this is the corresponding periodic pattern along time. If we change the coordinate from C1 to C2, the phase variation is amplified to delta phi 2. The corresponding periodic pattern is also amplified. Then we change coordinate C3 to C4, and finally C5. The phase variation is greatly amplified to 180 degrees. So we can get the key intuition that the amount of phase variation varies with different coordinates. And by changing the coordinates, or to say shifting the regions, we can amplify the target phase variation. Next, we take the interference into account. Here, the green arc represents the periodic movement caused by the target, and the blue spikes represent the combination of the interference. In coordinate C1, we only consider about a small portion of the target and the interference. We can see here the phase variation caused by the target is much smaller than that caused by the interference. And after coordinate shifting from C1 to C2, the target-induced phase variation is greatly amplified, and the interference-induced phase variation is suppressed. And you can see in C1, the phase is messed up by the interference, but in coordinate C2, we can see clear periodic pattern. So by coordinate shifting, we can amplify target-induced phase variation and suppress interference. The third challenge is the slow fading. Slow fading is a unique challenge associated with LTE signals, and we deal with it leveraging the wavelet-based filtering. Please refer to our paper for more details. After signal processing, we propose 2 example applications, which is respiration sensing for indoor environments and car speed estimation for outdoor environments to demonstrate the effectiveness and pervasiveness of our proposed system for both fine-grained activities and high-speed movements. We also have done some post-processing for 2 applications. For respiration sensing, we have some blind spot and orientation issues like in Wi-Fi sensing. We propose multi-base station combination scheme. And for the angle issue in car speed estimation, we propose a successive refinement to achieve better speed estimation. Finally, we have the evaluation part. For respiration sensing, we have USRP software-defined radio as our LTE receiver to receive the LTE signals. And we have done experiments in 2 scenarios, a home scenario and an office building with dense Wi-Fi deployment. The coverage of LTE-based pervasive respiration sensing is affected by how many watts the LTE signals travel through. When the LTE signal travels through 1 watt, the detection rate is 100%. When it travels through 2 watts, it is 92%. And for those rooms deep inside the building, for the 3 watt areas, it is 90%, which is 6 times larger than the coverage of Wi-Fi sensing. The right figure is the detection rate with and without coordinate shifting. So we can see that without coordinate shifting, the performance can decrease by over 50%. For car speed estimation, we have done experiments in several scenarios, including 3 roads and 2 parking lots. The LTE receiver is placed on the curb and the target is moving along the road. And you can see in all the scenarios, the average speed area is always less than 2 miles per hour, which is the requirement for commercial LiDAR devices. So we can see that our proposed scheme is as good as commercial LiDAR speed meters. This is the map with base stations and the experiments in our university. For future work, we are going to realize multi-target sensing using LTE advanced devices with more antennas. And we will improve our signal processing schemes to realize finer activity sensing. And we may also combine multiple LTE terminals to realize distributed sensing. In conclusion, we involve LTE into the ecosystem of RF sensing, and we address the unique challenges such as strong interference associated with LTE sensing. And we demonstrate the unique advantages for LTE sensing using 2 example applications. Okay, that's all. Thanks for watching.
Okay, great. Thanks for the great talk. Let's see whether we have some questions from the on-site audience. So we'll start with on-site audience. The questions there, then Slack, then YouTube. Okay, because there's a kind of a delay between your talk and the YouTube streaming. All right.
Right.
So if
Can I start? Hi, Andreas Beauty from ETH Zurich. Thanks very much for the interesting talk. I have 2 questions regarding your indoor sensing. Could you say again, you used the LTE base stations as like just normal LTE base stations, and you used an USRP for receiving, is that correct?
Yes.
Right. Regarding this coordinate shifting, does this mean you need multiple different receivers, or how do you actually do this coordinate shifting? That was a bit unclear to me.
Yeah, the coordinate shifting, we are doing some mathematical process. Let me check. Okay. You can, in a word, I'll try to be simplified. Okay, in a word, for LT sensing, okay, for the coordinate shifting, you can see here I have introduced the intuition of coordinate shifting. So we can by coordinate shifting to amplify the target and suppress the interference. So in detail, we are actually doing some, we are treated as an optimization problem, and we are using the gradient descent to realize the coordinate shifting to achieve a suboptimal result, which is not optimal, but it is enough for here to achieve a reasonable accuracy here.
Right, thanks. But it's purely processing. It has nothing. You still need a single receiver.
Yeah, I still need to have some LT receiver. Yeah, here is now we do not have some commercial LTE like LTE open like the open Wi-Fi chips. We do not have something like that. Yeah.
All right. So could you see, is there an advantage if you would have multiple base stations, which would give you this inherently without you having to process, or you could process even more if you would receive the signal from multiple different angles, multiple different attenuations?
Yeah, so we still propose, in the paper, we propose some multi-base station combination scheme based on their performance. Yeah, we do have some signal processing on that. Right. Yes.
Thanks a lot.
Yeah, thank you.
Great. Let's have a look about the Slack. Questions from Ray Xiao. I have two questions. What's the range of the sensing area of LTE? And if it's too large, the second question, if it's too large, how to differentiate the target user from the inference users?
Yeah, this is a good question. Yeah, for the first question, yeah, we do have a lot of results on the sensing range, and you can see here this one. This is a detail. This is a concrete scenario in a large conference room. Let me share this slide. The average, the sensing, yeah, and you can see here when the target is about 6 meters away from the receiver, the absolute error is still less than 1 BPM, which is considered to be a good performance. So we can see that the sensing range is 2 meters in this large room, reference room with windows. And for some cases, like some rooms deep inside the building, the sensing range, of course, decreases. Yeah. And the second question is, what's the second question? Sorry.
Okay, if its range is large, how to differentiate the target users from the interference users, like people walking around?
Yeah, in this room, yeah, if someone is walking outside this room, yeah, it will not affect a lot. But if somebody is inside this room and walking around the target, yeah, of course, it is hard to differentiate between the target, the tiny respiration, and the very huge the walking. Yeah, it's hard to differentiate. Maybe we still need to further signal processing to realize it. Yeah.
Okay, maybe second to last question from Yuanqing Zheng. Is it possible to do 5G sensing?
5G, yeah, the 5G protocol, yeah, I have searched on that. The 5G protocol is very different from the 4G, the LTE protocol. Yeah, the main difference is here in the 4G, in the LTE protocol, the reference signals are transmitted constantly, never stop, everlasting. But in 5G protocol, it is on demand. So probably we cannot use the same way here to realize 5G sensing.
Okay, last question. Also the last question for the session. From Xu Yuan, for LTE sensing, why do you consider phase difference rather than the amplitude with a single antenna? Second, how to address the interferences from the other cars? Right, that's the question.
From other cars? Oh, okay. It means the car scenario. Okay. Okay. The first question is sorry, what's the first question?
Okay, maybe you can just ask the first question and answer the second question offline. So yeah. Do you consider phase difference? Why do you?
Oh, okay. The phase difference and the amplitude. Yeah, sure. We can. Yeah, I do have done some experiments using amplitude. Yeah, during our experiments, we find that the phase variation can achieve a longer sensing range than the amplitude. Yeah, that's the main reason. And for the second question, in the car speed scenario, for other cars, yeah, I have some slides for that. Okay. Okay. As you can see here, this is the angle issue of car speed estimation when the real speed of the car is v, but we are actually measuring the v cosine theta. There's an angle between the movement of the car and the line connected the LT terminal and the car. So when there are multiple cars following each other, the theta are very different from each other. So the v cosine theta are very different from each other. So we can differentiate them.
Okay. Good. All right. Thanks, Yuda, for the great talk and a nice Q&A.
Thank you.
Having enough with this, let's just end this session, and I hope you can enjoy the rest of sessions of SenSys. All right. Thank you. Thanks for the attendance and watching. Bye.
Hello, everyone. Do we have all the speaker here? Hey, Jonas.
Hello, nice to meet you.
Okay, we can hear you well. That's good.
Amazing.
Abir, are you here? Abir and Tara?
Excuse me?
No, I'm asking
you're talking to the
the third and the fourth presenter.
yeah. I think I'm going to mute myself for a second.
Yeah, sure. Wang, do you want to test the speaker one and microphone one more time? I think you will be Wang Tang. Sorry if I mispronounced your name.
I think his video is frozen, right?
Yeah. I think there are about 20-second delay between Zoom and YouTube channel. So it's Abir. Abir Ahmad. Can you try to test your microphone to see if it works?
Yeah. Can you hear me?
Yes, I think that's good. Quang, could you please try to share your screen to see if it works? Professor Wang Tang, I think his video is frozen. Jonas, if there's a technical issue with the first presenter, can you go ahead and present first, just in case?
Yes, I will be able to do this.
All right, that's good.
Sure, you're welcome.
With the first presenter, can you go ahead and present first? All right, I think we can start now. Hello, everyone. This is VP Nguyen from University of Texas in Arlington. I'm sharing section 4, localizations. We will discuss 4 exciting papers in this section. So each presentation is 20 minutes in total, 16 minutes for the presentation and 4 minutes for Q&A. So there is around a 20-second delay between Zoom and YouTube. So please put your questions early in the chat. Right. So Wang Tang, are you ready? All right. So I think there's some technical issue with the. Okay, he's sharing the screen. Okay, good. But we cannot hear you. We cannot hear you. So can you try to say something?
Hello.
Hi, Tara.
Hi.
Are you ready?
I think I'm the last person to present, right?
Yes.
Okay, I just woke up.
Right, good morning.
Thank you.
We cannot hear you, Quang. So I think let give the first speakers a few minutes to fix the technical issue. So we'll go ahead with the second paper. So the second paper is a Snapper GPS algorithms for energy efficient, low cost location estimation using the GNSS signal snapshot. The presenter is Jonas Boykert. Jonas is the doctoral PhD. He is a PhD student in computer science at the University of Oxford, where he is supervised by Professor Alex Rogers. He focused on developing an open wildlife tracking system and also work on GPS mobile for mobile robotics. Go ahead, Jonas.
Thanks for the introduction. I hope everyone can hear me well. So yeah, this talk is about our Snapper GPS project. And with Snapper GPS, we aim to develop an open source GPS receiver with very low energy consumption and at very low costs, mainly for wildlife tracking. And our current version here, it can basically run several years on a single coin cell by using also very simple hardware to keep the costs down. And our paper here at SenSys is mainly about the fast and robust positioning algorithms behind Snapper GPS that allow you to still get an acceptable accuracy of about 11 meters in real-world applications. from the very, very rough data that this receiver spits out. Yeah, but I think at first I need to provide some background. So global navigation satellite systems, like the GPS, for example, they allow us to localize objects, humans, or animals anywhere on the Earth. Just as an example, biologists tag wild animals with GNSS receivers to track them and to learn about their behavior. However, traditional receivers have disadvantages in this scenario. They decode all the satellite signals and compute their location in real time on the device itself. So their signal acquisition and signal processing, they are computationally pretty expensive and they need a lot of energy. And if they run on battery, then their lifetime is quite limited or they are bulky just because the battery is large. And in addition to that, they also need from time to time longer visibility of the sky, which is just kind of a challenge when you track marine animals that surface only very briefly. And the energy consumption I just mentioned, that's also a problem for other applications, such as wearable fitness tracking, for example, or low-cost logistics tracking, at least certain types of it. Yeah, and then we have snapshot receivers. So snapshot GPS receivers, like Snapper GPS, for example, they just sleep most of the time. And they only wake up at defined intervals to record short snapshots of satellite signals, which kind of addresses all these challenges. And these signals that they capture, they do not process them on the device itself. Instead, what they do is they take the signals and digitize the raw signals and just store them. And then after you recover such a receiver, you just transfer its data to another computer, for example, in the cloud. And that one then estimates the receiver's position history. And this kind of eliminates any onboard signal processing as well as any real-time data transmission. And both together greatly lowers the hardware complexity as well as the energy consumption. So a few snapshot GPS implementations have been presented in the literature so far, but certainly several aspects are missing. For example, most of them have just been evaluated in simulations or on data from commercial GPS front ends, and they just naturally provide very good signal quality. However, you really want to build like tailored, simplified hardware for this to benefit from the very low energy consumption and the very low costs that this technique allows, at least in theory. So, for example, existing implementations require relatively high sampling rates of often like at least 16 megahertz. And then you also need several bits for the amplitude quantization. And instead, what our Snapper GPS receiver does, it uses a much, much lower resolution, just 4 megahertz sampling rate and 1 bit amplitude quantization for the captured snapshots. And this does not only reduce the amount of required onboard memory to store the snapshots, it also allows to capture the snapshots with the USART interface of a low power microcontroller that just runs on 16 megahertz. And all this together, it just greatly simplifies the hardware, which again reduces costs and energy consumption. Just as an example of this, hourly fixes, the Snapper GPS receiver here consumes just 15 milliampere hours per year. However, as I said before, existing snapshot GNSS algorithms, they are just not robust enough to provide reliable, accurate, and fast positioning based on these ultra low resolution signals that are captured by the Snapper GPS hardware. So our goal here now is to develop improved or even novel snapshot positioning algorithms that significantly increase accuracy and reliability for these segments. And for this, we use probabilistic signal processing. But at first, I think I need to talk a bit about traditional approaches to snapshot GNSS. So for this, let's go back to our snapshot GNSS workflow. So the main problem here is that the cloud segment that must estimate locations from very, very short signal snapshots, just 12 milliseconds in our case. And this is just way too short to decode like any payload data, for example, signal transmission timestamps. So we also do not know the signal travel times then, and hence also not the distances to the satellites. In consequence, we kind of must reconstruct these timestamps from just the raw snapshots. And for this, we have to rely on the unique periodic codes that all these satellites broadcast. And yeah, they have period lengths of like 1 to 10 milliseconds, which corresponds to like 300 to 3,000 kilometers. And what we're going to do is we're going to specifically look at the code phase. So the code phase is the shift between the start of a new code period of a certain satellite and the start of our signal recording. And this provides some information on the signal travel time. So to be precise, the code phase is the last fraction of the signal travel time. Let's say you could fit n.x codes between you and the satellite. Then you wouldn't know the integer number n, but the code phase tells you the last fraction x. And you can exploit this in basically two ways. So the first approach comprises two steps that are called satellite acquisition and course time navigation. And satellite acquisition estimates the code phases for each potentially visible satellite just from the raw snapshot. And then course time navigation reconstructs the full distances to the satellites and estimates location and time. However, existing implementations use non-robust least squares optimization for the latter, which kind of prohibits using very low sampling rates and amplitude resolutions, but you just have lots of outliers here. So our first improved approach to snapshot GNSS builds on a tailored acquisition stage and then uses Bayesian strategies to efficiently and robustly identify and remove the outliers that the acquisition stage provides. For this, we put priors on each satellite observation and use then an algorithm that is inspired by the run-stack algorithm that is, for example, often used in computer vision. And with this one, we quickly test different subsets of observations until we found one that is plausible. And then we also incorporate at this stage all other satellites whose code phases approximately agree with the solution from the tested subset. And in this way, we increase accuracy by incorporating more observations. However, unlike the traditional run-stack, we don't just randomly select the subsets that we test. Instead, we select them guided by their prior likelihood to be reliable. Yeah, and then we also have an alternative approach to this, which is novel. And that one uses robust maximum likelihood estimation instead of least squares optimization. Yeah, and here we model the code phase observations as like a mixture with normally distributed valid observations and uniformly distributed invalid measurements. And in this way, we jointly solve the outlier detection problem on the one hand and the final positioning problem on the other hand in just a single probabilistic framework. And here we also use maximum likelihood estimation to estimate certain error parameters of our low-cost hardware at first. For example, the frequency offset of the front end, which can be quite large. And knowing this one significantly speeds up satellite acquisition, quite important. Yeah, in addition to course time navigation in the literature, there's also an approach that does not separate snapshot GNSS into acquisition on the one hand and course time navigation on the other hand. This one is called direct position estimation, or sometimes also direct positioning or collective detection, just three terms for basically the same thing. And it just has a single step, as I said. It basically directly estimates the position of the receiver that maximizes the likelihood of observing the captured raw signal. So basically, you compare the signal that you would expect to receive at a certain point on Earth with the signal that you actually received. And then we have likelihood, and for the optimization of this likelihood, we take an existing algorithm that is based on branch and bound optimization, and then we tailor this algorithm to low resolution signals such that it runs faster and is much more robust. Specifically, what we do is that we integrate our consecutive code periods in the snapshots to increase the signal to noise ratio. And we also use more than one satellite system. So yeah, lots of algorithms, and we want to investigate which of these three concepts is best suited for ultra low resolution signals. So as I said before, 4 MHz sampling rate and 1-bit amplitude quantization. And yeah, let me just say, we also provide an implementation of all of these algorithms as like an open source snapshot GNSS algorithm compilation on GitHub for everyone to use. And yeah, then we take these implementations and do a real world evaluation of the algorithms with moving low-cost receivers in pretty diverse environments. And here below, you can see some cumulative, some empirical cumulative distributions of the resulting horizontal tracking errors. Yeah, we use different number of satellite systems and hence also different numbers of satellites here in the different columns. And basically what we do is we show that our outlier detection methods improve the success rate of course time navigation from 81% to 97% and reduce the median error from 50 meters to just 12 meters. And on the other hand, the algorithm runtime increases by only a few percent. And this accuracy here is definitely sufficient for many applications, for example, wildlife tracking. And yeah, our novel maximum likelihood approach, the second one from the previous slide, that has an even slightly better accuracy of just 11 meters. Unfortunately, its runtime is 3 times higher, but still pretty low. And then finally, the third approach from the last slide, the direct positioning algorithm that we implemented, that even achieves the same reliability of 97% while using less satellites. But so less satellites than the MLE, but unfortunately it has magnitudes higher runtimes. However, let me just say that this is still an improvement over state-of-the-art direct positioning, which is down here and can only calculate 20 fixes for 24% of our data, so fails most of the time. Yeah, and also let me know that in general, this evaluation here is the very first performance comparison where we have different snapshot GNSS algorithms on the same data. And we also make our data set, which has thousands of signal snapshots from a lot of different scenarios. We make that available to the public for everyone to study and everyone to use. Yeah, so to summarize, we have a purpose-built snapshot receiver, and we developed novel algorithms that allow us to operate it with an unmatched trade-off between costs, energy consumption, and performance. And the whole thing is accessible via a public web application and a cloud service that we implemented. And after the paper was submitted, we even went on to track some sea turtles in the Atlantic using our Snapper GPS system. Yeah, so that's it. Thanks for your attention. It was nice to have the chance to speak here and present our project. And I think since I have a few minutes left, I'm just gonna head over to our web application and show some exemplary tracks as an illustration. So here, for example, I've just been cycling and walking around Oxford, and each of these dots is like a fix that we calculated for a snapshot. All of these snapshots, just let me say that they were processed independently. So there is no smoothing or no filtering, also no cherry picking, data pre-selection. It's just every snapshot we recorded is processed here, and then the environment, as you can see, is quite diverse. So if you move to the city center, it's the uncertainty, which is represented by the circles, grows. And then if we move outside of the city, then to open fields, and the track gets smoother. Yeah, can also move on to a forest. But anyways, it's quite robust in general. So here, for example, for this data set, we get fixes for 99.8% of our recorded snapshots. Yeah, I think I also have some time to maybe show one of the turtle tracks. So basically, whenever these turtles here in the Atlantic surfaced, you got a dot on the map. This wasn't quite active turtle here, so really not much more to say about this. yeah, so this is our website. We can also use it to like configure a Snapper GPS receiver, or everyone can use it to configure a Snapper GPS receiver just in the browser. It works via web USB, so you don't have to install a driver or download like an app. So yeah, this is really just to make Snapper GPS accessible to like everyone. It's also an app for a phone which you can download to configure your receiver in the field. So such that really like everyone can use it, even if they're not a technology nerd. But yeah, I think finally I shall open up to some questions, and I would like to thank you again for your attention.
Right. Thank you very much for a very interesting work. Question from on-site audience, please. So let me start first. So moving forward, what are the main challenges that we need to address in order to deploy this system in the real wildlife tracking application? Can you give us some input about that?
Yeah, so that's a great question. That's all very present here. So we already had like one trial with actual animals, as you have seen, like the turtle trial, and we have demonstrated basically that the system itself works very well. So the GPS part of the system, but we had to learn that there's also a hardware challenge. You have to think about like, how do I design like this specific enclosure, for example, for this certain type of animal. So when you want to track another animal, you need to adjust your system again a bit, the hardware a bit, to make it suitable for this system. With a challenge like with a system like this, that you have to recover to get the locations. Obviously, one challenge is that you have to find the animal again. The advantage, obviously, is that the device then is just a fraction of the cost of like one device which would do real-time tracking. But you still want to think about how do you ensure that you have a high recovery rate. So, for example, for our first deployment, we deployed like 10 of these receivers on turtles, but then also we had like beach patrols. We got only 8 of them back. So maybe we want to add like an VHF receiver, for example, to make it easy for someone to like cover the tag because he knows that the turtle is actually coming.
Right. Thank you. So any question from the on-site audience again? I don't see any question from the Slack channel and YouTube. So if you have any question, please put it in. Right. Okay, so the second question is that I don't see you mention about the communication overhead. So what are the communication overhead? So for example, after it compute the snapshot, how does it communicate?
So the device itself doesn't have like mobile communication. So it just captures the data from the satellite and stores the data until the device is recovered. So if you would add like an LTE module or something like that, it's this will just be magnitudes higher energy consumption than the GPS module itself. So it would kind of it would render the whole idea kind of useless because this is so energy efficient now. So it's really made for recovering the tag and then plugging it in via USB to your laptop or to your smartphone and transferring the data then. And the data transfer can be done like even like 10,000 snapshots. You can do it in like seconds or a few minutes. So this is the way to go for this technology.
All right. Thank you. Let's thank the speaker again, everyone. So the first speaker, the second speaker, which is for the first paper of this section, is Wang Tang. So Wang, can you go ahead and share your screen?
Yeah, okay. Let me try to share my screen. Okay.
Let me give a little bit introduction. So the first paper of the section or the second is curve light, an accurate and practical light positioning system. And the presenter is Professor Wang Tang. So Wang Tang is a professor of computer science at Sun Yat-sen University in China, where his team focused on building mobile and embedded systems for various domains, such as smart facilities and robotics. So recently, he devoted a lot of his time to develop a light positioning system for industrial application with the deployment in the real production lines. So in this talk, he will introduce the designs and experience of their work. Wang, please go ahead.
Okay. Hello, everyone. Thanks to VP for the introduction. I'll be happy to present to you our recent work on a light positioning system. This is a joint work with Dr. Zhimeng Yin from City University of Hong Kong. Okay, so in this work, we want to build a high accuracy location systems that works for applications like robotics, autonomous driving, VR and AR, and the warehouse management. So in this kind of applications, we want high accuracy to centimeters or millimeters. This is must for a smooth or safe navigation and precise control. And at the same time, we want the localization to be done very quickly. It ensures instantaneous accuracy for moving device. So for example, imagine a robot that moves at a speed of about 5 to 6 meters per second, like the ones from ABB or Hukang. So if we have only 1 Hertz update rate, that means we will end up having a 5 meters error, which is unacceptable. Okay. So lastly, we want our solution to be low cost, so it can be scalable to large space. There are basically 2 approaches to localization in indoor environments. The first approach uses wireless signals. Wireless signals are pervasive, and there's no need of nano sight, but they suffer from interference, multi-pass effect, and so on. So the location accuracy is not very satisfactory. A second approach uses light signals, which are more predictable. So the location accuracy can be higher at the cost of line of sight, of course. Now, here is a brief review of our recent work, the recent work on light positioning techniques. From the perspective of the receiver, there are multiple ways to sense light signals. The first approach uses cameras. The camera is readily available on smartphones. So there's been a lot of work that use smartphone camera to capture the light signals to localize this device. The problem is that the working distance may be limited because the resolution is not very high for a smartphone camera. A second approach uses light sensor, which is very low power and low cost. And earlier methods used light intensity model, which turned out not to be very successful because of the intensity model is not very accurate. So recently, the researchers have mainly focused on using special light patterns. The recent work includes spin light, smart light, and so on. And our work falls in this category. The third approach uses markers. They can reflect light signals that to be captured by high-resolution cameras. This approach is chipless and batteryless on objects, but otherwise is expensive on the back end. And the last approach uses active receivers, mainly the laser radar that gathers depth information of the surrounding environment. This is the mainstream technique used on robots and the vehicles. Of course, the device is somewhat heavyweight and expensive. Now, this picture shows an overview of our system. On the ceiling is our transmitter. In the center of the transmitter is an infrared LED chip. The shade can rotate at a specified rate. On the shade, they are the transparent and translucent regions that allow the light signals to form particular patterns on the ground. So the receiver here can can obtain two angles, the theta angle and the gamma angle, by sensing the light signals. From these two angles, the receiver can localize itself. So the idea is quite simple. Now let's take a close look at the transmitter. So inside the transmitter, there's an MCU that controls the LED and the motor. The motor drives the shade to rotate at a specified rate. By default, the rate is 1,200 RPM. That is 20 revolutions per second. Also, we have a gear plane here that it's got many teeth on the edge. It works with an optical isolator to accurately track the angle that the shade has rotated so far with respect to some initial direction. So we can see that there are transparent and translucent regions on the shade that generate white and gray colors on the ground. So this creates a particular pattern on the ground. Also, the shade is divided into multiple sectors. Okay, so our final design has multiple sectors, but actually a single sector can do the localization job. So we first focus on a single sector case. Here, this picture shows the layout of a single sector, which spans 90 degrees on the shade. There are 4 types of regions. First is sector gap region that is used to delimit the different sectors. And then the sector ID region used to identify a particular sector. And we also have white curve region and a gray curve regions. These 2 regions is divided by a curve, which is the key element of our design. Okay, so on this curve, the receiver, when this receiver moves away from the origin, it can see a longer arc length. The gray arc. It will see a longer gray arc. So the characteristic of this curve is that to ensure that this arc can be uniquely determined by the length of this arc. Okay, so on the ground, each point has a unique combination of theta and r. So once we have the theta and r, we can determine the location of the receiver. Another concept of our design is a location frame that encodes signal segments corresponding to the 4 regions. Let's have a look at an animation here. We have receiver A and B, and the sector has a projected image on the ground that moves across the 2 receivers. This creates 2 location frames on receiver A and B. We can see these 2 frames have 2 different light patterns. And from the length of this particular segment, the type 4 segments, we can determine the length of the gray arc and hence r, the distance from the origin. Okay, and furthermore, the offset of the start points within a location frame determines the theta offset. Now we have the theta and the r, the distance. We can determine the location of the receiver. Okay. So why do we need multiple sectors? This is because we want a higher location update rate. In our 4 design, we divide the shade into 4 sectors. So each of the sectors can do the localization independently. So with a single round of rotation, we can obtain multiple location samples. This helps us reduce latency and improve accuracy as well. Here we have 4 receivers on the ground, A, B, C, D, and they receive 4 different location frames with different patterns. Again, we can find the length of each segment. Here we see that location frame is a bit longer than the previous version because they now span more than a sector. Okay, but the basic idea remains the same. Now let's look at the curve. So how does the curve affect our system performance? An ideal curve should better tolerate inaccurate signal boundaries caused by, for example, motor jitters, signal noise. So we have formulated this problem into an optimization problem. The goal is to minimize average location error in covered area, subject to several constraints. For example, the gray arc length should grow with distance r. So this is one of the opticity requirement. And there are also some physical constraints of the shade. To simplify the problem, we approximate the curve with a sequence of 9 segments. We then search for an optimal set of such 9 segments and then use a curve to fit these 9 segments. Okay. Now this figure shows that our curve compares how this compares with classical functions like sine or log. So it shows that our curve performs the best in terms of location error. So this is an implementation of the system. So first, the transmitter has a diameter of 12 centimeters. Here in the picture, the outer cover is removed. We can see this shade here. It's a plastic shade that can absorb about half of the light energy. So from this view, the top view, we can see clearly the 4 sectors. Okay. A single transmitter can cover an area of up to 10 meters radius and generating location at 36 Hz rate. Now, this is our receiver. It's got several components. First, the front end. On the top of the front end is the light sensor. Beneath it is an FPGA board that processes the light signal. And then we have an MCU that transmits the data to the backend. The backend is responsible for configuration and data fusion and communication with a computer, for example, on a robot. A receiver can have multiple sensors connected to it to improve accuracy and also partially overcome obstruction. So this is our test room. Okay. Now the overall accuracy is about 2.6 centimeters error during night and daytimes. We also examine the effect of distance and using multiple sectors. First, at a larger distance of 8 or 9 meters from the origin, the error increases to about 5 centimeters. This is, of course, expected because the SNR reduces when the receive moves far away. But in all cases, the error remains below 10 centimeters. Also, we can see using multiple sectors helps with accuracy, especially at a large distance, because using multiple location samples helps reduce the effect of noise. We've also done some additional experiments, including the effects of ambient light and reflection from nearby objects. We also tried to connect multiple transmitters to cover large areas. 3D localization is possible without design if the device is covered by more than one transmitters at the same time. We've spent much time on verification of our system in production environments. So in the following, we will present our experience with 2 use cases. The first case is autonomous valet parking. So the task here is that the self-driving car in a garage needs to find a parking place in the multi-floor garage. The problem is that it has only one IMU module on board. And of course, the error will build up as time goes on. So our task is to help the vehicle to correct the IMU regularly and to keep the location error below 5 centimeters. We deployed 20 transmitters over an area of more than 3,000 square meters. On the right, we can see our receiver with 2 sensors underneath the windshield. Okay. So in one of the experiments, we wanted to see the effect of our system in reducing IMU drift. So in this case, the car travels in a loop. Without our system, at the end of the loop, the trajectories will drift apart. So see these blue lines. Okay. Now we have installed 5 transmitters along the way. They can correct the IMU regularly. So the trajectories at the end of the loop, see the red lines here, are brought very close together. So the distance is now smaller than 1 centimeter. Okay. And the second case is warehouse automation. So our system is used a component of robots, a hybrid replication system to provide a global location service while other methods like LiDAR fail. Okay, there are all kinds of factors that affect the effectiveness of individual method. So here we have our receiver on top of the robot, and it's got 2 sensors placed on the 2 sides of the robot. Since its adoption, the robot never got lost again. It's been in continuous operation for more than a year. To summarize, we have developed a light positioning system that achieves high accuracy in realistic environment. It's got low latency that allows smooth tracking of moving robots. It's low cost and practical. It's verified by its production environment. And we are still optimizing the accuracy for more advanced tasks like robotic grasping. Okay, so this is my talk. Thanks for listening. Questions are welcome. Thank you.
Thank you, Juan. Very great, great work. Any question from on-site audience, please?
Hi, this is Andreas Beauty from ETH Zurich. I have a brief question regarding, you had this slide where you had multiple bars with 1 sector and multiple sectors.
Yes.
I was wondering, does this matter in general? Because as far as I see, it's just you increase the sampling rate with this. So I think it was slide 15 approximately, where you were showing there was a bar with only 1 sector you used. Exactly that one, 13. Could you go to slide?
Yeah, 31, right? 31, right?
Exactly.
Yes.
They had 1 single sector and multiple sectors. So I would assume that multiple sectors only help if you have a moving target. Is that correct? Or how can you explain the differences? Because it's increasing the sample rate, as far as I understand.
Yeah, if when the sampling rate is high enough, we can fuse the location samples, assuming that the robot moves at only a low to medium speed. So we can add up these location samples, and this helps to reduce the effect of the noise.
So what was the average moving speed you had for these experiments?
It's about, let's say, so here we assumed a maximum speed of commercial robot of 5 to 6 meters per second. So the experiment, in our experiment, the speed was below 2 to 3 meters per second. It's not very fast, but it's working speed.
Do you also have any numbers for stationary targets? Do you know how accurate you can be there?
This are the results of stationary device. So we place the device on the ground and measure the locations, and this is a result of a static device.
Okay, thank you very much.
Thanks.
Right. So we have time for one more question. Okay, let me. So in your presentation, you briefly talk about converting 2D localization, which is the current result, into 3D localization. Can you elaborate a little bit more about what would be the main challenge for you to realize such a 3D localization system?
Okay, so the extension from 2D to 3D is not very difficult in principle here. We can see what we do is actually to determine the ray from this chip to the receiver. So when we have more than one transmitters, we have two rays that intersect at a 3D location, right? So the principle is simple. It's just the challenge is that we need more dense deployment of the transmitters, and that could be a problem too in some scenarios.
All right, right. Thank you very much. Thank you, Quang, again. Right.
Thank you.
Abir, Ahmad, are you ready?
Yes.
All right. So please share your screen. So this next speaker is Abir Ahmad. Abir will present the paper enabling passive backscatter tag localization without active receiver. So Abir is a CS PhD student at Stony Brook University. His research interest is backscattering-based communication system. He works on different applications that can be enabled by backscattering system like object tracking and localization, ambient intelligence, structural health monitoring, and so on. Please go ahead, Abir.
Hi, I'm Abir. The title of the paper I'm presenting today is Enabling Passive Backscatter Tag Localization Without Active Receivers. Other authors of this paper beside me are Shao, Milutin, Akshay, Petar, and Samir. Backscattering implies a passive radioless form of signal transmission achieved by reflecting an external RF signal. Such transmitters do not require an onboard radio, which allows them to be batteryless, tiny, and inexpensive. These properties make backscattering devices highly suited to the ubiquitous IoT vision, where all objects in our surrounding space carry such a device in the form of a tiny tag. However, almost all present-day backscattering systems, from standard radio frequency identification or RFID to other advanced technologies presented in the literature, rely on active radio-based devices on the receive side of the backscatter link. Such active receivers possess significant signal processing ability and thus are power hungry and much more expensive in relation to tags, thus posing a scalability challenge. A massive scale, ubiquitous deployment is always limited by the number of these active devices that can be reasonably deployed. The way to address the scalability issue is to enable passive reception of backscatter signal directly on the tags themselves, thus eliminating the need for separate active receivers. This enables direct tag-to-tag communication and in turn multi-hop tag-to-tag networks. In this paradigm, the external excitation signal to backscatter comes from an ambient source or an intentionally deployed radio. These research efforts have demonstrated the basic communication ability of passive tag-to-tag networks. With more traditional active radio-based systems, the tag localization approaches gain significant support from the capabilities of the active receivers. Without such receivers, these approaches do not directly apply to passive tag-to-tag networks. The overarching goal of this paper is to develop such functionality. Let us first see what properties of wireless signals are and how they are related to distances, which can enable ranging and in turn localization. Let us forget about backscatter for now. Suppose a wireless signal is transmitted by the blue antenna and the red antenna receives the signal. For the sake of clarity, let us just consider the signals exactly at the antennas. Specifically, two things happen to the signal: change in amplitude and change in phase. Both amplitude and phase are related to the distances. The phase is directly proportional to the distance mod 2 pi. It is ambiguous because of the phase wrapping effect. In practice, it is relatively accurate. Amplitude is inversely proportional to the distance. Unlike phase, it is not ambiguous. However, in practice, it is highly susceptible to noise and hence not a good indicator of distance. Because of this, localization systems generally use phase and not the amplitude for localization. Even though it is ambiguous, channel diversity can be used to perform accurate localization. These techniques are widely discussed in the literature. Let us go back to passive backscattering now. The amplitude and phase have similar properties. There are no known techniques for passive phase estimation. Amplitude can be determined passively. Our work develops a passive technique for phase estimation to perform accurate localization. Let us look at a tag-to-tag communication link. We have an exciter, which could be an ambient source or an intentionally deployed radio. This signal travels to the backscattering tag. The signal gets reflected from the tag and reaches the receiving tag. Influencing the pattern of reflection is the mechanism for transferring information. The receiving tag also gets the signal directly from the exciter. These two signals interfere with each other. The receiver decodes the information by looking at the interference pattern. There are three channels here: exciter to tag channels, whose phase is denoted by θ1 and θ2, and tag to tag channel, whose phase is denoted by theta. We are interested in the tag to tag channel's phase. Let us look at how the signals interfere. For the sake of simplicity, I represent sinusoids as points rotating around a center. The radius is the strength of the signal. The blue curve is the exciter signal at the receiver, and the red is the backscatter signal. These two signals interfere with each other. When these sinusoids are added together, we get another sinusoid with a different amplitude and phase. In this animation, I have the same blue and red dot as before. However, there is a green dot. This is same as the red dot, except that its center of orbit is the blue dot. This directly tracks the sum of the signals. Notice that the amplitude and phase of the green signal is different and is dependent on the relative phase and amplitude of the interfering signals. For easier visualization, let us represent sinusoids in a different way. I already demonstrated that sinusoids can be viewed as points rotating around a center. We can imagine a coordinate system which is rotating itself so that the points appear stationary. The benefit of this coordinate system is that now we can represent sinusoids as vectors. The length of the vector is the strength of the signal, and its phase is the angle from the horizontal. Hence, the resultant signal is just the vector sum of the individual components. With this simplified picture, let us see how traditional tags communicate. Most tags influence the angle of the red signal. This is called phase shift keying. This leads to change in length of the green vector or the signal strength as viewed by the receiver. This can be used to signal information from one tag to another. If, instead of a tag, an active receiver were used, it would have access to all the information in this graph, the length and angle of all the vectors. However, a passive device can just measure the length of the green line, which is exactly where the data is encoded. In other words, a passive tag can just measure the signal strength. Even though backscattering tags transmit using phase shift keying, the receiving tag still sees an amplitude modulated signal. In order to enable our localization technique, we propose to have more than 2 phases on the tag. This part of the tag consumes negligible power compared to the rest of the components. So, the overall increase in power consumption of traditional tags to have more than 2 phases is negligible. For the sake of simplicity, let us assume that the tag has perfect control of the phase. This can be viewed as the tag's ability to rotate the red vector. Notice that this rotation can be viewed as a sinusoid. This sinusoid is something that a passive tag can see just by measuring the received signal strength. Hence, calculating the phase of this signal is something a passive device can do. This can be done by a very small matrix multiplication followed by a lookup table on passive tags, the details of which can be found in our paper. This phase is equal to theta plus theta 1 minus theta 2 mod 2 pi. Now we can reverse the roles of the tags to get a similar equation but from the other direction. That can be given as theta plus theta 2 minus theta 1 equals to that other constant mod 2 pi. From these two modular equations, we can find out theta, which is the tag-to-tag channel's phase. In order to evaluate our technique, we developed prototypes of passive tags with discrete components. This is the green colored board in the picture. The transmitter or the modulator part of the prototype of the tag is a switch that connects the antenna to multiple capacitors and inductors. In an IC version of the implementation, this would consume about 150 nanowatts of power. However, one of the throws of the switch connects the antenna to the receiver or to the demodulator part of the circuit. The IC version of this module would consume less than a microwatt of power. This is just a simple circuit that measures the received signal strength. These modules of the tag interface with a low-power microcontroller. The control logic in the IC version of the tag would be under a microwatt. So, the whole tag would operate in less than 2 microwatts. This is comfortably in the range where enough power can be harvested from RF signals alone. For data collection, we interface the microcontroller with a PC or SD card. This is just for experimentation and data collection purposes. For excitation, we used a circularly polarized patch antenna connected to a signal generator. In this experiment, we evaluate the performance of our passive technique for tag-to-tag channel phase measurement. We place 2 tags in an environment and increase the distance between them and measure the phase. This is the graph on the right. Notice that our method closely follows the theoretical model shown in the dotted line. Most of the error does not come from the passive nature of our tag, but actually comes from the multipath effect. This experiment is just like before, but we also measure the channel phase using a commodity RFID reader and tag as well. we kept the environment roughly the same as much as possible. Notice that the error in phase is in the same ballpark as measured by passive tags or active receivers. Here, 10 degrees error in phase correspond to about 1 centimeter error. The median phase error is between 10 and 20 degrees, which corresponds to 1 and 2 centimeter respectively. In this experiment, we demonstrate that we can isolate the tag-to-tag channel from the excited-to-tag channels. We kept the tags at the same location but moved the excitation source. This drastically changes the excited-to-tag channels, but the tag-to-tag channels roughly remain the same. Consider the graph on the right. Notice that the tag-to-tag channel phase roughly remains the same. There is about a 20-degree variation, whereas the excited-to-tag channel varies drastically, where the variation is more than 100 degrees. Just to recap, the phase of the signal can be written as the following equation. Theta equals to 2 pi d over lambda mod 2 pi. Here, lambda is the wavelength of the signal, which is about 33 centimeters. What we have done in the previous slides is determine theta mod pi, and hence we have an estimate of the distance as the following equation. T equals to theta lambda over 2 pi plus a non-negative integer multiple of lambda by 2. We can represent ambiguous distances as probability distributions. Consider the picture on the left. The yellow dots are the positions of the anchors. We know ambiguous distances from these anchors. The possible location of the tag are concentric circles around each anchor. These are the white lines in the picture. In order to account for the noise in the readings, we blurred the image. This is the image on the right. This approximates the probability distribution of the position of the tag. We localize the tag based on the most likely location. Our algorithm is iterative, which means that localized tags are used as anchors for localizing further tags as well as improve the performance of the ones that have already been localized. In order to evaluate our localization technique, we imagine a network of tags placed randomly in a 4 by 4 meter area surrounded by anchor tags on the parameter. We assume that the error in measurements is statistically similar to the ones measured experimentally. We evaluate the localization performance at different anchor and tag densities. This is shown in the blue curves here. The red curve is our baseline. It is the first iteration of the localization algorithm in which no tag-to-tag measurements are used, just anchor-to-tag measurements. Notice that the blue performs better than the baseline. This highlights another important aspect of our system. Unlike a reader, we draw leverage from measurement of order of n squared channel links, where n is the number of tags, whereas a reader will have access to just order of n links. To conclude, passive devices can just measure signal strength. For localization purposes, phase of the signal is more reliable than mere signal strength. We develop a passive technique for channel phase estimation, which can be used to perform ambiguous ranging. Our experimental results show that passive phase estimation is as accurate as estimation using active radios. Link diversity leads us to localization. Our seed system achieves sub-centimeter median accuracy of localization. Any questions?
Thank you, Abir. Very interesting work. Question from the audience, the on-site audience, please.
Hi, thanks for the interesting talk. Rong Sen from McMaster University. I just wonder, like in the case that you have many tags in the space, do you expect some kind of collision avoidance mechanism needs to be adopted?
All right, so in our paper, we discussed some of the protocols that we would need in order for have some sort of arbitration for channel access. But the important thing to notice there is that the number of packets that need to be transmitted is not n squared. So not every pair of tag has to communicate with like every other tag. Just one broadcast is enough to measure the one-sided channel phase, and another broadcast is enough for all of the other tags to measure that phase from the other side. So yes, you're right that there'll have to be a channel access mechanism, but the communication overhead is not too much, not excessive.
I see. Thank you.
Any other questions from the audience?
Thanks, very good. Andrew Markham from University of Oxford. I was just wondering whether you can use phase stitching to resolve the phase ambiguity. So multiple frequencies, basically.
Yes, so we tried that, doing that. So the rate of change of phase should be proportional to frequency. If you increase the frequency, the phase changes linearly. But in practice, the amount of frequency diversity that you need in order to enable that is much more. So for example, in ISM band, we did experiments from 902 to 928 megahertz. And in a normal environment, this frequency was not enough to perform a centimeter scale localization. If one had access to a huge bandwidth, then yes, potentially that could have been the case, but not here.
Okay, great, thank you.
You're welcome.
Right. Right, let's thank Abir one more time, everyone.
Thanks.
So the last paper of localizations at SenSys this year is R-Fusion, robotic wrapping via RF, visual sensing and learning. And it will be presented by Tara Poroshaki. So Tara is a PhD student at MIT Signal Kinetics Lab. Her research focus on fusing different sensing modality through artificial intelligence to enable new capabilities that were not feasible before across robotics, augmented reality, and smart manufacturing. So please go ahead and start the presentation, Tara.
Thank you for the introduction. Hello, everyone, and thank you for being here. I'm Tara Poroshaki from MIT, and today I'm very excited to share with you my work on robotic grasping via RF visual sensing and learning. This is a joint work with my collaborators, Isaac, Mergen, Alberto, and Fadl. Over the past few years, we have seen advances in robotics. People have been building robots that can see and understand the environment, similar to how we humans do. But this talk is about something different. It's about how can we build robots that can see things that we cannot see. How this allows them to understand and manipulate the environment in ways that humans cannot. In this talk, I will show you how we built a robot system that can do exactly that. Let me show you a video with our robot in action. So here is a hidden key under a pile. And the robot has a camera on its wrist. Many of today's robotic systems use cameras. But the camera cannot see the hidden key because of its line of sight to the key is blocked by the items in the pile. In fact, in the bottom right, you can see the camera's view, and you can see that the key is not visible. In this talk, I will show you how a robot can locate the key, declutter its surrounding, grasp the key, and then declare that it has found the keys for you. Here you can see the robot in a completely new environment when it is searching for remote control. It will grasp the remote control, hand it over to you, so that now you can watch your favorite show. In this talk, I will be telling you about our system, which we call our Fusion. It's a fully integrated robotic arm that enables grasping objects in line of sight, cluttered, and fully occluded settings. Our system introduces the first RF visual reinforcement learning framework for robotic retrieval and manipulation. I will also show how the system is highly accurate and efficient, and it achieves 96% success rate in retrieval tasks. But before I tell you about our system, let me tell you about some of its applications. One of the applications is in warehouse automation. Today, there is a huge interest in using robotics for processing orders in e-commerce fulfillment or processing returns. In many of these scenarios, robots need to retrieve a specific item from a pile, but today robots are limited to their line of sight, and they become very inefficient when their target item is occluded under the pile. In contrast, our system can find items even when they are in non-line of sight, and this makes processing orders and returns much faster and helps address multi-billion-dollar challenge in industry. Another application is in manufacturing, where the robot might need to retrieve a tool in cluttered environment to finish its task. A third application is in future smart homes, where we envision robots that can find and retrieve missing items for you. This will be specifically helpful for the elderly and people with disabilities. These are just a few examples of our system's application. Now let us discuss how our Fusion works. Our system relies on batteryless UHF RFID tags, such as the one you see here. They cost as little as 3 cents. And as many of you know, you can read an RFID tag using an antenna. The antenna sends a signal that powers up the tag, and then the tag responds back with its unique identifier. Over the past few years, we have seen a number of systems that use this response to estimate the distance between RFID tag and the antenna. This distance is not enough to localize, but it will tell us that the tag is on a circle centered at the antenna. But since one single circle is not enough to localize, what today's systems do is that they add multiple antennas in different locations. And where these resulted circles intersect is the location of the tag. In fact, this is a standard RFID localization approach that relies on multiple antennas that are spaced far enough apart, sometimes taking up even to several meters of space. Unfortunately, it is very hard to put such a big set of multiple antennas on a robotic arm. So we started thinking about whether there is a way that we can use a single antenna on a robotic arm and still localize the tag. And to do this, our idea was to leverage the arm's mobility to collect measurements from different locations and localize the tag. Let me tell you what I mean by this. Let's assume we put this antenna on the wrist of a robotic arm. It takes a measurement, moves to a new location, takes another measurement, and moves again until we have enough measurements to localize the tag. In principle, this idea would work, but there is a problem. The problem is that the noise in the RF measurement introduces an uncertainty in our distance estimations. This means that instead of the tag being exactly on a circle, it's somewhere on a ring. The problem is that because of these rings, instead of the tag location just being a single point, it can be anywhere in this area. This area can be as big as a pile of objects or even your whole workspace. And with this level of uncertainty, the robot won't be able to find and retrieve the hidden target object. This is a well-known phenomenon, which is called dilution of precision. And one way to overcome this is to move the antennas further apart. And let me show you how it helps. When we move the antennas further apart, you can see that the intersection, which is the possible region for the tag location, becomes smaller. This large separation between the antenna reduces the dilution of precision and allows us to locate the tag with higher accuracy. But there is a problem with this approach. It requires the robot arm to move over a longer distance and makes the process less efficient, and it makes it slower. And if you think about the application that I talked about before, like the warehouse, you want the orders to be processed as fast as possible. So now we are left with one of these two options. If we take RF measurements from locations that are far from each other, the localization will be more accurate because of a small dilution of precision, but it will take longer to finish the task and the system will not be efficient. On the other hand, if we take RF measurements from closer location, the localization will be less accurate because of a large dilution of precision, but the system will be more time efficient. So we started thinking, is there a way to achieve high efficiency and high accuracy at the same time? The key idea is to use RF visual reinforcement learning to enable accurate and efficient localization. Let me tell you what I mean by this. We fuse RF and visual information from the wrist-mounted camera to minimize the uncertainty about the tag object location. This will help our system to be more accurate. And we will use reinforcement learning to choose the optimal measurement location, and this will help our system to reduce the time it needs to collect measurement and makes it more efficient. Let me tell you what I mean by fusing RF and visual information for minimizing uncertainty. Remember that the antenna on the wrist of the robot takes an RF measurement and estimates the distance from the robot gripper to the RFID tag. This estimated distance tells us that the object can be anywhere on a spherical ring with radius d. This is what we can get if we only rely on RF measurements. And here where vision comes in. We have a depth camera on the robot whose depth information can be used to create a 3D model of the scene. Then we can intersect this model with the spherical ring from RF measurement. Once we do this, we can eliminate most of this spherical ring, and we are left with these few regions, which are the possible tag locations. While I was able to minimize my uncertainty about the tag location from a whole sphere to these small regions, I still don't know where the exact tag location is, and I need more measurements. Now the question is, where should the robot move to take its next measurement? Here is where reinforcement learning comes in. In reinforcement learning, an RL agent decides on its next action in order to maximize its reward. In our scenario, our robot needs to decide on its next vantage point while maximizing its efficiency. To begin, our robot gets an observation from the environment and uses this observation to determine its next vantage point. Based on the efficiency of this action, the robot will then receive a reward. And this process repeats until the target item is localized. Now, the difficult question is, how do I extract an observation from the environment? In traditional vision-based system, the norm is to feed all of the camera's visual data to the RL agent. But in our system, we also have RF data. So how do we feed both of these RF and visual data to the agent? For this, we have designed an RF visual encoder that encodes information in two ways. Remember that we extracted possible regions for the tag location through RF visual fusion. But RF visual fusion alone is not enough because it relies heavily on vision, and we want our system to be robust to errors in both RF and visual sensing modalities. So we additionally need to somehow include RF information into our observation. Recall from earlier, then we can quantify an RF uncertainty using dilution of precision. This can be computed using a closed form equation, and we use it as an input, as an observation from the environment. In the interest of time, I will not go into the details of these equations, but together, RF visual fusion and this dilution of precision form our full observation encoding. In putting all this together, RF visual reinforcement learning is able to optimize the trajectory while enabling accurate localization. Now that I have shown you how the robot can accurately localize the tag, there is one final step. The robot needs to perform grasping to retrieve the item. First, the robot moves above the localized object, but remember it cannot see the object. If we use a state-of-the-art grasping network, it shows us all the places that we can grasp. Usually these regions are represented as a heat map where the red shows areas with a large probability of successful grasping. But unlike vision only based system, I don't want to grasp just anything. Remember that I know where the tagged item is under the pile. So the robot can focus on grasping in the vicinity of the tagged object. And by doing this, the robot can remove the clutter around the tagged object area, and it keeps grasping until eventually it uncovers and retrieves the target item. It can verify that it has picked up the right item by reading its RFID information. It will then hand it over to you so that you never lose your keys again. To implement this system, we customize a universal robotic arm with an Intel RealSense depth camera and a log periodic antenna that were mounted on a robotic two-finger gripper. The antennas are connected to two software-defined radios, and the signal processing and computations are performed on an Ubuntu machine. The RL agent that we talked about is a deep Q network that is trained in simulation using VREP over 11,000 iterations. Now let us look at some of our results. Remember that our system needs to accurately localize an RFID tag. We tested our system over 400 experimental trials, and we tested the localization accuracy with different tag orientation and location. And we tested it in line of sight, fully occluded, and multiple pile scenarios. Here I'm going to show you the CDF of the localization error. The x-axis shows the localization error in centimeter, and it is in logarithmic scale. And I plot the x, y, and z error separately here. You can see that the median error is less than half a centimeter. This means that our fusion achieves centimeter level accuracy, and it does it without requiring an antenna array. Another goal was to have an efficient system. So we compared our system's performance to a baseline that takes RF measurement from a 2D array of predefined vantage points. These vantage points are in a way that the robot achieves good localization accuracy. But because the system does not use reinforcement learning to increase its efficiency, you will see how the results are different for this baseline. Here, I'm going to show you a graph where the x-axis is the travel distance of the gripper from the initial position of the gripper until its first grasping point. And the y-axis is the CDF. So the baseline that is shown in orange travels more than 2 meters to localize and reach the grasping point. While our system that leverages RL and RF visual fusion is shown in purple and has a 90th percentile, which is less than 2 meters. The graph shows that there is at least 2 times improvement in the efficiency because of our methods. Let me show you one last result about our system end-to-end success rate in retrieving an object. For this, we evaluated our system in different scenarios. In scenarios where the requested item is in line of sight, we ran 10 experiments where the objects were scattered in the workspace and 10 where there was a pile. And our system was successful in retrieving the object in all of these experiments. And in scenarios where the requested item is not in line of sight, we ran 10 experiments where the objects were divided into 1 pile, 2 piles of the same size, and 1 big and 1 small pile. Our system was successful in retrieving the object in 9 out of 10 of trials in the first 2 scenarios, and it finished all of the trials successfully in the last scenario. Overall, it shows that our fusion success rate is 96%. This high success rate is because we are fusing 2 different sensing modalities which can complement and correct each other. What is very important here is that our system has a high success rate even in non-line of sight. This is where traditional vision-based systems either fail completely or take significantly longer to search for the target item. So in this talk, I presented our fusion, a new robotic system that enables efficient and accurate object localization and retrieval. I also showed you how our fusion works in line of sight, non-line of sight, and occluded settings. And I also told you how our fusion introduces fundamental and new RF visual primitives for fusion and reinforcement learning. And what I find very exciting about this work is that on one hand, it can enable new capabilities that were not possible before, which opens up new application, e-commerce fulfillment, manufacturing, and smart homes. And on the other hand, it combines techniques from various areas, including robotics, reinforcement learning, and RF sensing to enable these tasks. For more information, you can visit our website. And with this, I want to thank you all for listening, and I'm now open to get questions.
All right, thanks, Sarah. Very nice talk. Question from the audience, please.
Thank you for the very interesting talk, Rong-Sam from Master University. I'm just curious, what is that 1 out of 10 case that your system failed in the non-outside scenario? What are the reasons for failure for your system?
That's a very good question. So our system also used a state-of-the-art grasping network. In those 2 trials that our system failed, the problem was that the system localized the object, but the grasping network failed to grasp anything in 3 tries back to back. So that was when the system declared failure and said the grasping network failed to grasp anything. So the problem that caused the failure was not our contribution, but was that the grasping network that we were using we're not completely successful in handling all the scenarios for grasping.
I see. Thank you.
Right. There's a few questions from the Slack channel. Let me read. The first 2, maybe you can answer the last one in the chat later. So the first question is, what happens if there are multiple RF tags in the box? Does it increase the uncertainty? Right, that's the first question. The second question is, how do you define reward for reinforcement learning? Okay.
This is a very good question. So for the first question, if you have multiple tags in the environment, if you want to localize one of them, you can use the select function in the RFID protocol and select which of these RFID tags you want to take measurement from. So when you take measurement, only that specific RFID that you're looking for will respond back to you, and you will localize that single RFID. If you want to localize all of them at the same time, you can take measurement from all of the three of them back to back each time, and then you can localize all of them at the end. So it depends on what you want to do. But the system can handle when there are multiple RFIDs in the environment. And for the second question, the reward function. So remember that we wanted our system to be efficient and accurate to localize. So after the robot in simulation was able to localize, we rewarded the system based on the travel distance that the robot took from when it started until it successfully grasped. So if the robot was traveling a longer distance, it would get rewarded less. And it was traveling a very shorter distance and we're able to find good measurement location, we would travel it, we will reward it better. So over time, it will learn that what is the good path that it should take to minimize its travel distance and maximize its efficiency, while being able to get measurement locations that helps it to accurately localize faster.
Right. So let me try to read the last question as well. Please try to answer briefly, and then you can give more detail in the chat. So could this help rescue victims of building collapse after an earthquake using our GSM signals instead of RF tags?
So the problem with rescuing people in a collapsed building is that when the building collapses, the walls are not built like the thick walls are gonna make it very hard to get response back from the RFIDs if you have RFIDs. So I don't know if we can use RFIDs or the RF frequencies like for that, but maybe we can do it with other frequency ranges that can have better penetration over the collapsed building materials. So I don't think that specific robot that is trying to grasp items can be helpful in helping victims in a collapsed building, but probably in future people can come up with designs that can use this RF visual primitives like fusion and reinforcement learning and make systems that can achieve that goal.
Right. Let's thank Tara one more time, everyone. So this also concludes the sessions. So enjoy the remaining sessions in SenSys, everyone. Thank you.
È per questo che domani chiamo la tizia e dico: guarda, noi abbiamo bisogno di un contratto con le deadline entro cui diciamo quali stanze effettivamente blocchiamo. Però poi le deadline gliele dobbiamo dare noi. Quindi dobbiamo fare il template con la registrazione. Early, io pensavo addirittura di fare 3 step invece che 2, cioè non fare early e late, fare, che ne so, autori, early per tutti gli altri e late, perché gli autori glielo puoi chiedere immediatamente, devi fare un giorno dopo. A quel punto sai, sempre assumendo che possa essere altri, quelli che non hanno persone. È ovvio che a quel punto, se gli dai le 2 opzioni, come è successo qui, vuol dire che implicitamente stai già annunciando il tuo libro. Però il problema possiamo anche semplicemente dire che la auto registration è quella, indipendentemente che sia presenza. Se io ho l'opzione di stare a casa, perché se sono cinese, mi partono.
Hello, everyone. Welcome to Sensys Technical Session 5, Knowledge-Driven Machine Learning for Sensing. My name is Xujia, and I'm going to be the session chair for this session. So we have 3 great papers in this session. And for the local audience, please step up to the microphone at the end of the talk for your questions. And for the remote audience, please feel free to post questions in the conference Slack channel and the chat for the YouTube. And please feel free to do so before the talk ends. So with that said, let's welcome our first speaker, Ray Xiao. Ray, do you want to share your screen?
Sure.
So Ray is a second-year graduate student in computer science at Zhejiang University, where he is advised by Professor Jingsong Han. Previously, he has also worked as an undergrad research assistant in Sense Lab led by Dr. Jun Han at the National University of Singapore. His research interests revolve around wireless sensing and cyber-physical security. Welcome, Ray.
Thanks, Shijia, for introduction. Hello, everyone. My name is Ray. I'm a second-year graduate student from Zhejiang University. I'm glad that I could present our work, Wi-Fi, one-shot recognition for unseen gesture via cat Wi-Fi. So this is a joint work with Jianwei Liu, Jingsong Han, and Kui Ren. Human gesture recognition is a key enabler for many human-centered applications, such as virtual reality, medical control, and smart home automation. Traditional gesture recognition approaches have their respective shortcomings. For example, wearable sensors is uncomfortable for users. Camera-based solutions may raise privacy leakage concern. Compared with them, Wi-Fi-based solutions are promising because they are contactless, privacy-preserving, and also ubiquitous. Wi-Fi-based gesture recognition works following the supervised learning scheme, which is basically composed of 3 phases. First, we need to predefine base gestures. They are the gestures that we want to recognize. Then, we need to get training samples of each gesture. And finally, a machine learning model will be trained to recognize these base gestures. The model can provide accurate recognition on these base gestures once well trained. Okay, now here comes the question. What if now we want to recognize unseen gestures, which are not included in base gestures? Apparently, the model couldn't recognize unseen gestures since these gestures are never trained. However, unseen gestures are actually important and worth consideration in real-world deployments. This is because predefined base gestures cannot keep up with ever-evolving demands. Also, it is crucial to allow the user to adapt their system to their own preference. However, in existing systems, to recognize unseen gestures, we still have to follow the supervised learning scheme. That means we have to first collect training samples. The user has to perform the gesture for tens of times, which is absolutely laborious. Then the whole model has to be retrained, even if we want to introduce only one single new gesture. So this traditional supervised learning scheme raises 2 kinds of overhead: data collection overhead and training overhead. Therefore, the limited scalability of the existing systems asks for a new scheme to update the gesture they could recognize. So here comes our problem definition. Assume that our system can recognize a few base gestures. Then, when introducing unseen gestures, it is possible that user only need to collect one signal sample for any unseen gestures. And the model can fast adapt to new data without retraining the whole model. In the literature, this problem falls into the category of few-shot learning, which means learning with a few samples. In the real world, it is actually common that you want to recognize something when you've literally never seen it. And a human can do this really well. For example, a man may recognize a panda after seeing one picture of it, even if he has never seen a panda before. But why? This is because human beings have a large amount of prior knowledge. Although he has never seen a panda before, he has seen a lot of other animals like dogs, cats, and so on. So future learning basically works in a similar way. In future learning context, we call a training set a support set, and a testing set a query set. We use a support set to train a model. Remember, our assumption is that we have a base data set. Although the base data set has no overlap with support set, it could provide prior knowledge about data distribution and help to train the model. So if we could bring adequate prior knowledge from base data set, the model could recognize query samples of unseen gestures, even if there are only few support samples. So in mobile sensing area, there are some brilliant existing works adopting meta-learning as their future solution. Here we give a simple view of meta-learning. Briefly, in normal supervised learning, the aim is to train a learner model. In meta-learning, the aim is to train a meta-learner, which guides the training process of the learner model. So here is an example. The meta-learner should be trained over a variety of learning tasks and optimized for the best performance on the distribution of tasks. That's why meta-learning is also called learning to learn. So following this scheme, MetaSense proposed that Sensei 19 adapt their sensing system to new users and new devices. ArfNet proposed that Sensei 20 adapt their ARF sensing system to new environments. So can we also directly adopt meta-learning and achieve one-shot gesture recognition? Unfortunately, the answer is no. There are two main challenges. First, the insufficient prior knowledge. The base data set in Wi-Fi gesture recognition system is really small. Therefore, the prior knowledge in base data set is insufficient. To illustrate this, we collect samples of 20 gestures as base data set and apply meta-learning algorithms using MetaSense and ArfNet to recognize unseen gestures. The result is far from satisfying. Both of meta-learning solutions can only achieve accuracy higher than 50%. And if we further reduce the base class number to 6, the results become even worse. Therefore, directly applying meta-learning cannot fulfill our goal. Second, the meta-learning scheme is very complicated. As aforementioned, the model should be trained and optimized over a variety of learning tasks. Although meta-learning alleviates the training overhead on unseen gestures, it intensifies the regular training process. Therefore, the training overhead still exists. In our work, we want to alleviate the training overhead from a fundamental level. So we propose OneFi, a one-shot recognition system for unseen gestures. OneFi is basically composed of 3 parts. First, we propose a data augmentation method to enrich the prior knowledge. Second, instead of using meta-learning, we propose a similarity-based one-shot learning framework. Additionally, we propose a self-attention-based backbone to further alleviate training overhead. We first introduced our data augmentation scheme. The key idea is that when a database dataset is small, we could create additional synthetic gesture samples that do not exist in base dataset. So the intuition here is that we could create a push left gesture by rotating a push forward gesture. For example, we collect a sample of push forward and compute a Doppler spectrogram as a model input. But now, how can we know spectrogram of a rotated gesture? Apparently, directly apply rotation on a spectrogram doesn't make sense, because while this signal is inherently symmetrically different from viewing data, here we require signal modeling. We compute the velocity distribution of the gesture and apply rotation on the velocity domain. So please refer to our paper for more details. Here, the left side shows the virtual gesture push left we create, and the right side is a real gesture collected by a Wi-Fi AP. We can see that the created virtual gesture is nearly identical to real gesture. Therefore, we can enrich our prior knowledge by using our virtual gesture generation method. Now, we introduce our one-shot learning framework. Our framework is composed of 2 stages. The first stage encodes prior knowledge from base dataset into a feature extractor. Our method is to train the feature extractor together with the classifier C1 as a multi-classification task. Note that C1 here is only used in stage 1 to help train the feature extractor. Then in the second stage, we fix the weight of the feature extractor and fine-tune a new classifier C2. This fine-tuning is quite simple. Basically, each row of C2 is a feature of a support sample. The function of this classifier is to compare the cosine distance between the query set and support set in the feature space. Our one-shot learning framework is lightweight because only a new classifier C2 needs to be fine-tuned based on cosine similarity. So it significantly alleviates the training overhead. Finally, we introduce our self-attention-based backbone of our feature extractor. Our backbone is called Wi-Fi transformer. The biggest benefit of using it is that it utilizes self-attention mechanism, which allows for more parallelization than recurrent networks like ARSTM, and therefore reduces training times. Here is a high-level presentation of its workflow. So let's first take a look at the transformer encoder, where most of feature processing is done. A key component of it is the multi-head attention module. It is entirely built on self-attention mechanism. Inside this block, all the processes are done in parallel. We use this attention mechanism to substitute the traditional sequence-aligned recurrent architecture and therefore boost the training speed. Now, let's turn to the position embedding module. The Wi-Fi gesture data are essentially time series data. Therefore, the position and the order of time patches are important. We add this module to account for the order of timestamps in the input sequence. Note that we also attach a special classification token to represent the meaning of the entire sequence. In brief, the advantage of Wi-Fi transformer is that it only needs O1 sequential operations, while recurrent architecture needs ON sequential operations. Therefore, using Wi-Fi transformer reduces the overhead of training the feature extractor. To evaluate our system, we implement a prototype using desktop with Intel 530 network card. We use 1 transmitter and 4 receivers. The sensing area is 2 times 2 meters squared. We collect 40 different types of gestures and split them into 2 parts, 20 as base gestures and 20 as unseen gestures. First, we compare the overall accuracy of Wi-Fi with that of the existing few-shot learning works. In one-shot setting, Wi-Fi could achieve an accuracy of 84.2%. It outperforms both MetaSense and ArcNet. The reason is that apart from its specially designed one-shot learning framework and Wi-Fi transformer backbone, the proposed virtual gesture generation technique improves the overall accuracy, especially when the base dataset is small. Then we evaluate our data augmentation method, the virtual gesture generation. So we expand our base dataset by 12 times by creating virtual gestures. In this part, we compare the virtual gesture generation with 2 baselines without using data augmentation and a naive augmentation, adding Gaussian noise on signals to augment data. So we vary the number of base gestures. A smaller base data set means a harder problem. From the figure, we can see virtual gesture can effectively enrich the prior knowledge and improve the recognition accuracy. One of our goals in our paper is to reduce training overhead. As aforementioned, our system requires no retraining for unseen gestures. In this experiment, we investigate how much time it requires for our system to converge to its best performance on the base dataset. The experiment shows that training Wi-Fi for 8 seconds gives an accuracy higher than training MetaSense and ArfNet for 2000 seconds, showing Wi-Fi entails significantly this training overhead. To investigate whether Wi-Fi transformer could further alleviate training overhead, we do this experiment again, varying the backbone of Wi-Fi. The experiment shows Wi-Fi transformer help to relieve the training overhead, as it can converge within 2 minutes. Due to a time limit, we give a summary of other evaluation results. First, by adding more shots, Wi-Fi can achieve high accuracy in 20 unseen gesture classification. Specifically, our evaluation shows that 3 shots for each class can give an accuracy higher than 70%. Second, we investigated the impact of the number of receivers. It turned out that Wi-Fi works well even with only 1 or 2 receivers. Finally, our cross-domain experiments show Wi-Fi generalizes well. Here comes our conclusion. We designed Wi-Fi, a one-shot Wi-Fi HDR system. Extensive experiments shows its strong ability to recognize unseen gestures. We present a novel virtual gesture generation technique that significantly enriches the prior knowledge. And we designed a lightweight one-shot learning framework together with a self-attention-based backbone to alleviate training overhead. So that's it, and thank you for listening, and I'm open for questions.
Thank you very much, Ray. It's very interesting work. I think we have time for one short questions. Any question from the local audience?
Hello, I'm Shu Hong from UC San Diego, and thanks for your nice talk. Can you please go to the page where you show the query and the support site in computing the distance?
Here?
Yeah, so can you please go into detail on how to fine-tune the new classifier C2 as the query? So for the query side, do you have the true ground truth label for that?
Actually, the query feature, the query set means the testing set. So we should know it's ground truth, right? Because we want to test if it's correct. But if we want to fine-tune the classifier C2, we only need the support set. And this fine-tuning is quite simple. As I have already explained, each row of the classifier C2 is a feature of a support sample. So we just need to compute the feature of each support sample and put it in each row of the classifier, and that's it.
Okay, thank you.
Thank you.
Great. Due to time limits, I think we'll need to move on to the next speaker. But there are still some other questions that you probably can find in the YouTube chat.
Sure.
So please, thank you very much again, Ray.
Yeah.
Now let's welcome our second speaker, Huatao Xu. Huatao is a first-year PhD student from Nanyang Technological University. He has broad interests in ubiquitous computing, especially in wearable-based human activity recognition and localization. Welcome, Huatao.
Okay, thanks for the introduction. Can you see my screen?
Yes.
Okay. Let's get started. Hello, everyone. I'm Huatao Xu. Happy to be here and present our work, Limubird, unleashing the potential of unlabeled data for IMU sensing applications. Nowadays, most mobile devices have equipped with IMU sensors. They are accelerometer, gyroscope, and magnetometer. They facilitate many potential applications like human activity recognition, human-computer interaction, and indoor localization. To implement those applications, most existing models learn representation from IMU data in a pure supervised way. However, such a method has a big limitation. It requires a large amount of label data. Label data are expensive and hard or even impossible to collect in some cases. but unlabeled data don't have those disadvantages. So we ask, can unlabeled data help IMU sensing? To the best of knowledge, TPN is the first work that learns representation from IMU data. It first applies random transformation on the accelerometer data, and the shared CNN connect with some task ahead a chain to recognize whether the input signal has been applied those transformations. If you visualize the input in the data space after the transformation, it may look like this. And we think the CNN can guarantee that the representation can still hold those relations in the feature space. So it actually is a dimension reduction method. And our experiments show that this method's performance is not stable, especially in the multiple sensor cases. And as a new topic in machine learning domain, self-supervised learning methods has attracted a lot of attentions, and they can also utilize unlabeled data. There are many types: contrastive-based, game-based, and auto-encode basis. Among them, there is a very famous and successful work called BERT. It can learn representation from unlabeled text data, and those representations are very helpful to the downstream NLP tasks. And in our understanding, we think there are three underlying assumptions in BERT. First, there are large amounts of unlabeled data, like the Wikipedia, the news, or the books. And second, there are specific patterns in the text data, such as the grammar, the context, or the word meaning. More importantly, the patterns can also help many NLP applications. And at the same time, we also have some observation for IMU sensing scenario. First, there are also abundant IMU data. For example, we can easily access the IMU reading in the Android platform. And second, there are specific patterns in IMU data, like the periodic changes. IMU data contain rich information about the user behaviors. The last point, the patterns can also help sensing applications, such as the activity recognition. So in summary, we think IMU sensing scenario are somehow similar as the NLP scenario. So we want to introduce BERT to learn representation from IMU sensor data. We design BERT IMU plus BERT, named as linear BERT. Okay, next, before diving into the details of linear BERT, I will first introduce BERT so you can have a basic understanding. BERT has two phases. First, pre-training phase. The goal is to learn representation from labeled text data. It designs two methods. First method, we randomly mask some words or token in a sentence. For example, welcome to ACM SenSys. We randomly mask the word to, and next we transform the sentence into vector and feed them into the BERT model and generate the representation. A classifier is trained to reconstruct the masked word to. And for the second method, we first randomly sample two sentences and connect them with some special token. Another classifier is also trained to discriminate whether the two sentences are subsequent or not. So by the two methods, BERT can further learn the context information in the text data and generate effective representations for them. And in the next phase, fine-tuning phase, we can learn to accomplish a task with some labeled data. Let me take a sentence level task as an example. The input is a sentence, the output is class. The application includes sentiment analysis. For example, we input a comment, I like this t-shirt, into the BERT and generate the representation. A task classifier is trained to recognize whether this comment is positive or negative. So that's the whole process of BERT. We summarize in this figure. And go back to IMU sensing. Now we want to replace the input data with IMU data. But unfortunately, we find that the original BERT would fail due to the following reason. First, IMU data are continuous variables. So we don't need the diction component, and we also need some changes in the classifier and the mask approach. Second, IMU data are multimodal data. I mean the different sensors. So we need some adoptions on the BERT model and the representations. The third point, IMU data are motion features. So we argue that the second method is not suitable for IMU sensing applications. The reason is that there exists a frequent and natural transmission in the human behavior. So train the model to discriminate whether two IMU data are subsequent or not does not introduce any benefit. The last point is about the efficiency. The original BERT is supposed to run on the server equipped with powerful GPUs and CPUs, but for linear BERT, we hope it can run on mobile device efficiently. So we need some optimizations. Okay, next, I would like to introduce our methodology one by one. First, we will normalize the IMU data and try to mitigate the impact of multimodal. The problem is that IMU sensors has varied distributions. Previous works has proposed many solutions like mean variance, min max, magnitude, and FFT. But we find they all lose some important information in IMU data, like the value range or the magnitude, and the relationship between the three axes. So we propose our solution. It's simple but effective. The accelerometer values are divided by the gravity constant, and the magnetometer readings are normalized with the magnitude. Our goal is to narrow their distribution difference, but try to maintain the information as much as possible. The second, we propose a fusion method before we input the IMU reading into the BERT model. The first step is how to align those data. Thanks to the specific collection way of IMU data, we can easily assess the IMU readings at the same time step. So they are naturally well aligned. In this paper, we represent them in a single metric, just like the figure shows. And the second is how to fuse them. We also find the number of IMU feature is very limited. For example, the feature number is only 6 if we only adopt the accelerometer and the gyroscope. So to further fuse them and get more hidden features, we project the input data into a higher space with a metric multiplication. And those features are further normalized with layer normalization, which is widely utilized in the NLP models. And the gamma and beta in this equation are learnable parameters. So the model can learn how to dynamically normalize those features. And the next point, we made some changes on the training methods to solve the problem caused by the first and the third point. As I mentioned before, we adopt the first method and skip the second one. And the reconstruction task here is treated as a regression problem since IMU sensor data are continuous. And third point, we choose to mask continuous readings for each time. And the N is sampled from a geometric distribution. The behind reason is that due to the motion mobility, the neighboring IMU readings may have very similar values. So the model may treat and just simply copying the neighboring readings for reconstruction. So to avoid such a situation, we choose to mask multiple readings for each time, just like the right figure shows. So we can make the chaining more challenging. And for the last point about efficiency, we design lightweight models to solve this. We first downsampled IMU data to reduce the sequence length. We adopt 20 Hz, and our experiments show that 20 Hz is enough for many applications. Second, we reduced the feature dimension from 1024 to 72, which can help shrink the model size. Third, we adopt a cross-layer parameter sharing mechanism. So in linear BERT, we have 4 virtual model blocks, and only the parameters of first block are trained and those parameters will be shared with other blocks, so we can improve the parameters efficiency. Okay, put all the previous design together. Here is the workflow of linear BERT. It also have two phases. First, self-supervised learning phases. The goal is to learn representation. Starting from the normalized data, we first random mask some IMU readings and feed them into a projection and norm component, which is a fusion measure methods introduced before. And the linear BERT can generate representation after the hidden feature go through the purple block for several times, which implement the cross-layer mechanism. And in the next phases, we will utilize linear BERT to generate representation for some label data. And we can select a subsequence from the IMU sequence if you want a high granularity. And based on those representation, we can chain some lightweight classifier to accomplish some IMU sensing tasks. Okay, to evaluate our framework, we choose 4 widely used open data sets. And for each data set, we divide them into training, validation, and test set. The training set is used to train linear BERT without label, and we randomly sample a tiny portion of labels to train the classifiers. For the models in comparison, we implement linear GIU, which is based on our framework. And 3 models are from the previous work. RGIU is applying the GIU classifier directly on the raw data for comparison. As for the application, we choose human activity recognition HAR and device placement classification DPC. The second application is to recognize the position of the device, whether they are put in the pocket or in the hand. Since the 2 applications are all classification tasks, we adopt accuracy at F1 score for evaluation. Here are the overall performance with 1% label samples in HAR. And we can find linear GIU can achieve better performance than all the baseline models in all cases. And we also change the number of label samples. In this example, we can find linear GIU, represented by the green line, can outperform all the models in all cases too. More importantly, if we want to get the same accuracy, we find linear GIU only requires much fewer labels. And here are the overall performance in the second application. We find the results are very similar. And to further understand the performance of linear BERT, we visualize the representations in the low dimension with TSNE. We can find the same representation, the representation from the same class are very close. Such cluster effect is very beneficial to the downstream tasks. And finally, we also compare the number of parameters, the model size, training time in the server, inference time in a smart device with all the models, and we find for linear BERT or linear GIU, the computation overhead are affordable for mobile device. So for conclusion, we present linear BERT in this project, a lightweight representation learning model for mobile IMU sensor data. It can extract effective and generalized features and does not require any label data. More importantly, it is lightweight and can run on mobile device with low overhead. Extensive experiential linear BERT can significantly boost the performance of downstream models with few label samples. And we also made the source code publicly available in the GitHub. You can take a look if you're interested. Thanks for listening. I would like to take any question.
Thank you very much, Huatao, for the very interesting work. Is there any question from the local audience? So we do have a question from the YouTube channel from Kevin who asked, can you explain more on the fusion part? If the input dimension is 6, then there is a fully connected layer whose dimension is bigger than 6? Do you think this will learn a sparse knowledge? Thanks.
Okay. I think, as I mentioned before, the feature number of IMU sensors is very limited. So the clone number of the raw input data X may be only 6. So we want to get more hidden features. We utilize such methods, utilize a metric manipulation to expand the feature space. And this process is implemented by a linear layer.
Thank you. And there's another question in the Slack channel from Guohao Lan. Thanks for the presentation, a very interesting work. Would you please kindly share your insights on the advantages of BERT-based design when compared with the other semi or unsupervised learning methods for IMU-based recognition? Say, contrastive learning. From your experience, what are the biggest benefits of BERT-based design in your task?
Okay, I think that's a very general question. I'm still studying it. I can share some of my thoughts. Let me go back to the slides. So as we introduced before, there are many types of self-supervised learning methods. So we choose a very famous one. I think it's just first step for the IMU sensing applications. We can also try other types of self-supervised learning methods such as contrastive based, and I think it's a very new direction for the mobile sensing. And as for the benefits of the BERT, I think it can the most power point is that they can learn contextualize information in the with the unlabeled data. So no matter in the text data or the IMU data, I think they can also do that, and that's very important.
Yeah, thank you, Huatao. There's another question from Yuan Qing. Thanks for the great talk. Can LIMU BERT be trained to recognize unseen human activities?
No, currently no. I think it's a limitation of the classifier. So how do we train the classifier to implement those application? But it's not a limitation of the linear BERT. It's actually the encoder. So if we want to utilize linear BERT for recognizing unseen activities, we should have some special design in the classifier side, not the BERT side.
Sounds great. Thank you so much. Thank you again, Huatao. Due to time limit, we're going to move on to our last speaker. So Shuhen, do you want to share your screen? So Shuhen Li's research interest lies at the intersection of cyber-physical system and the data mining. He is interested in different IoT systems, including wearable sensors and smart buildings. He focused on developing machine learning methods that automatically uncover an innate pattern of sensory time series data, and he's looking for a summer internship. So if you guys like his talk, please feel free to send him an email then. Welcome, Shuhen. Shuhen, sorry to interrupt. Your sound is very weak from the remote side. Can you unmute? Local session manager, could you please help with
Hello?
Yeah, that sounds great now. Thank you.
Okay. Hello, everyone. I'm very glad to introduce our work unit, short-time Fourier-inspired neural networks for sensory time series classification. I'm Shuheng Li from UC San Diego, and this is co-work with Ranak Roy Chaudhary, Professor Jingbo Shang, Professor Rajesh Gupta, and De Zhihong. I'm very glad to be the first one to show the work in person.
Sorry, Shuhan, your streaming view is a presenter view.
Okay. So intelligent IoT systems equipped with sensors collect a large number of data every day. And one of the most important problems for these systems is sensory time series classification. And typical tasks include human activity recognition, seizure detection, building occupancy detection, and so on. So for traditional machine learning workflows, it will involve 3 phases: data pre-processing, feature extraction, and designing the machine learning model. However, upon environmental changes, one will need to recalibrate the feature extraction method and the machine learning algorithms. Well, if the data or the task change completely from the 3-axis MU data to the brain strobe EEG data, researchers will have to design from scratch. So traditional workflows require heavy duplicated manual labor. And recently, with the advance of deep neural networks, deep learning techniques are potential to generalize well. However, as a summary of recent deep neural network models, among the 4 types of data: motion data, medical sensing data, wave signals, or ambient data, these recent works mainly focus on just 1 or 2 types of data. So if we have a new task or a new data set, researchers will have to experiment on the previous deep learning models one by one, and that will take a much longer time for computing, and it takes a lot of sources for computing as well. So it motivates us to think about, can we design a neural network model that is unified to all the tasks? We do not want any model recalibration if we change the environment or change the data type, and it should ideally perform as well as domain-specified models. However, it is definitely not a trivial problem. And the issue is some data suits the temporal domain, like the motion data or the ambient data. Usually, when you look at just one timestamp, you can know some physics meanings of this data. Well, some data suits the frequency domain better, like the EEG data or wave signals. You will need to convert them to the frequency domain and then look at the frequency axis. Well, some data sets are noisy, and different data sets may have different sampling rates. The sampling rate difference can be very distinct. And so it's inspire us to think about doing time frequency domain analysis. And one of the most natural approach is short-term Fourier transform. So STFT conducts Fourier transform within a sliding window, and it generates a 3D spectrogram like this. It has both a time domain and the frequency domain resolutions. For the time domain resolution, it is maintained by the sliding window. And for the frequency domain resolution, it is maintained within the sliding window. That is, we do not have very fine-grained time domain resolution inside the windows. So for STFT, the benefit is that the weights are explainable and insightful, but the problem is they are fixed still. And they cannot be updated in a data-driven manner. If we have a new task or different data sets, we will need to design compatible filter or window function for STFT so that to fit this new problem. Well, on the other hand, convolution is very similar as STFT. It also conducts linear transform within a sliding window. And the benefit for convolution is that the weights are learnable. And the problem is they are initialized randomly, and we cannot get any insight from the convolution kernel weights. So this inspires us to developed a Fourier-inspired convolution. That is to just combine the benefits of these two modules. For the Fourier-inspired convolution, FIC kernel, the Fourier weights are used as the initialization of the convolution weights, and it is also used in the deep neural network pipelines so that the weights can be updated in a data-driven manner. So before we go into details, okay, change it. Okay. Okay.
Yeah, you can go.
Oh yeah. So before we go into detail of where we use this Fourier-inspired convolution, we'll firstly introduce the formulation of the problem. Let's take the human activity recognition as an example. And in these data sets, we have 5 sets of sensors, and each set of sensors has 3 types of sensors: 1 accelerometer, 1 gyroscope, and 1 magnetometer. It measures the quantities in the space, so it has 3 axes. That is, we will have 5 by 3 by 3, 45 channels in total. And we are interested in classifying the example sampled within a time range, let's say 256 in our case. Firstly, I will introduce how to model the one channel of the input X. Here we proposed a temporal spectral encoder that is composed of a temporal path and a spectral path, modeling the time domain and the frequency domain information separately. And in the spectral path, we will use the previously mentioned Fourier-inspired convolution. That is, the convolution weights are initialized by Fourier weights. And after the FIC model, we proposed a virtual filter that just selects the most important K virtual frequency channels. By important, we mean the absolute value of these frequency channels. And here we use virtual because the FIC is different from static SDFT. The output of FIC is similar as frequency transformed spectrogram, but they are just virtual frequency channels. And remember that different data require different time domain and time frequency domain resolution to capture the hidden pattern. That's why we also propose to combine with the temporal path and the spectral path. So in the temporal path, we use the resolution preserved convolution. It is just like an ordinary convolution layer. It is initialized randomly, but the only requirement for that is it has the same size as FIC, so that the output of the 2 paths can be concatenated together, and which is the output of the temporal spectral encoder. After getting the virtual spectrograms for each channel, they will be fused and concatenated together and fused by the 1D convolution, so that we fuse these different sensing channels together and to get a fused feature, hidden feature. So an overview of our model is, for the input X, we split it by channels and model them by the TS encoder. Next, we will fuse this output of these different TS encoders, and then use a ResNet model to model the fused hidden feature. However, another problem is that how can we decide the optimal window size and the stride size for the convolution operations in the TS encoder? Usually, different data sets will require different step size, stride size, or window size, and we do not really want to decide it by just exhaustively experiment on it. So here we adopt the idea of inception network and design a multi-scale branch with different TS encoder size and compatible ResNet depths, so that different scaled branch should have the same output size, and they can be concatenated and feed to a fully connected layer for classification. And for evaluation, we evaluate our model on 4 public datasets across different sensing domains. So the first one is a motion data set. It has the motion sensors we mentioned before, and the draw is for activity recognition. And the next one is a seizure detection data set, where the input data is branch drop EEG data. And the next is a Wi-Fi data set. It's a data set for RF sensing, and the draw is also for human activity recognition. And the last one is CATI data set. It's a building ambient data set that has the CO2 readings, temperature readings, humidity, and light intensity readings. And the draw is to detect the human occupancy in each room. And we summarize the statistics of the data sets here as a table. And we can see that the sampling rate across different data sets is very distinctly. For evaluation metrics, we use accuracy and FN score, which is computed as this, to evaluate our model's performance. Here shows the main result of the evaluation. And most of the compared baseline models are recent deep learning models that exist in top conferences. And we can see that our model achieves the best performance in average. Here, we use the bold to represent the best result and use the underlines to represent the second best result. Our UNIS model performs the best in the motion, the Wi-Fi, the CATI data set, and is the averagely the best model. And we perform the second best in the seizure data set, but the difference between the best model is just 0.4 point. Next, we evaluate the importance of different modules in the TS encoder. So we consider the following variants for ablation study. The first one is without the temporal path. We delete the RPC kernel. And the next is without the frequency, the domain. We remove the spectral path, FIC, and also the virtual filter. And the third one is without the trainable sightings. We replace FIC with static STFT modules. As shown here, all of these variants will degrade the performance, which shows the importance of our designed modules. And we also evaluate our model's robustness to the change of data sampling rate. As shown here, we always use the blue colors to represent our model in this page. And our UNIS model will compare with the other two best performing models. And we can see that our models is robust to the change of data sampling rate and to the change of input sample size. And also it's robust to the random additive noise in data, which is simulated by adding additive noise, which is controlled by a noise intensity, and also the missing values in data. You can see our model can perform the best or comparable the best results comparing with other baselines across different data sets. Next, we will discuss the usage of our model and the training behavior. So the first one is about using FIC, the Fourier-inspired convolution, as a feature extraction module separately. So here we propose that the trained FIC model can replace STFT. We put a simple experiment on that, which is we input the raw data by the extraction method and then feed to the ResNet model for classification. And here we compared our FIC layer with STFT, and we show that the trained FIC layer outperforms STFT significantly. Next, we discuss the explainability of our model. We study the effect of FIC with changes after the training. Here, we visualize the trained FIC weights, and the red part indicates that FIC highlights these channels, and the blue part indicates the FIC undermines these channels. We can see this visualization results corresponds to our intuition that most of the useful information in signal data is in the low frequency parts, but there are some useful information in the high frequency parts, maybe about the noise patterns or something else. And our branch 8, the branch with the highest frequency domain, frequency resolution can capture that. And next, we discuss the hyperparameter tuning issue with our model. Since one may have the question that the multi-scale branches, how will the multi-scale branches affect when we tune the hyperparameters? And here we will show that actually this multi-scale branch can help the model achieve decent performance and without any need of exhaustive hyperparameter search. We can see the general trend that by increasing the number of branches, the model can perform gradually better. And if one wants to achieve even better results, one can also exhaustively search on the hyperparameters. And we can see in the Wi-Fi dataset, the 7-branch settings or the 5-branch settings outperforms the 9-branch settings. In our previously mentioned experiments, we just use the 9-branch settings. We do not tune the hyperparameter for the models. And as a conclusion, we proposed UNIS, a unified framework for sensory time series classification with a novel TS encoder, a virtual spectrogram fusion strategy, and multi-scale strategy. Evaluate on 4 different data sets from different IoT domains and achieve the state-of-the-art performance. We conduct ablation study on different components of our model and study the robustness of our model. Furthermore, we verified the explainability and hyperparameter tuning issue of our model, and we argue that FIC can be used as a feature iteration module. And thanks for your attention. We will release the code and dataset after the conference. Any questions?
Thank you very much for the interesting work, Shuhan. Any question from local audience, please? So we have some questions in the YouTube channel. Kevin Hu asks, hi, I'm wondering for binary tasks, say KT data, do you compare how much more computational cost is added with your model comparing to other lighter model who are worth yours? If there's more cost, do you think this is worthy? Thanks.
Yes, we actually studied the cost of the computation, and comparing these baseline models, our UNIS model can can complete the whole training within 2 hours, and it is not the most time-consuming models. Here, I think TH80 model and RFNet model are much more time-consuming than our model, and it is just a 9-branch setting. And if one want to make it time saving, then we could try some lower branch settings, and that will be helpful for accelerating, and the performance drop will be not much.
Thank you very much for the answer, Shuhan. Thank you again. So due to time limits, this will be end of the session 5, and we'll move on to the next session. Let's thanks to all the speakers for the wonderful talk and the interesting work. Okay, have a good day. Bye-bye.
Okay, I give you back your pen. Yeah, don't worry. I will tell Professor from. Sí, ya están.
Hello.
Good afternoon.
In network sensor systems. We're joined by 4 great panelists. We have Nikki, G, Pei, and Gian Pietro. Let me just give you a brief intro of each of our panelists. We first have Nikki. Nikki Dragoni is professor at the Department of Computer Science in Oxford, heading up the Cyber Physical Systems group. Her interests lie in the tight integration of sensing and machine intelligence for context inference, control, and HMI. She has applied her work to a number of application scenarios, including mobile autonomy, asset monitoring, and localization. Nikki has founded and acted as director of the AIM CDT. In 2015, she founded Navenio Limited, deep tech Oxford spinout on infrastructure-free positioning, and a 2020 KPMG Best British Tech Pioneer. And in 2020, she won the CTO of the Year Award at the UK Women's in IT Awards. Next, we have Ji Lu is a chair professor at Harbin Institute of Technology in Shenzhen in China, and the dean of its AI Research Institute. Before joining HIT, he spent 18 years at Xerox PARC and Microsoft, where he was a principal research manager and partner of the company. His research interests are in sensor networks, AI for IoT, and energy efficient computing. He is the steering committee chair for CPS IoT Week and also for IPSN. He has received IEEE TCCPS Distinguished Leadership Award and 6 Best Paper Awards from top conferences. He is also an IEEE Fellow and an ACM Distinguished Scientist. Pei Zhang is an associate professor in the Department of Electrical Engineering and CS at the University of Michigan. His early work on ZebraNet is considered one of the seminal works in sensor networks, and his recent work focuses on structures as a sensor to infer occupant information through hybrid learning of physics and data models. Pei's work has resulted in several Best Paper Awards, as well as the NSF Career Award, Census Test of Time Award, and Google Faculty Awards. In addition, his work has been featured in popular media, including CBS, CNN, NBC, Science Channel, and Scientific American. Gian Pietro Pico is a professor in the Department of Information Engineering and Computer Science at the University of Trento in Italy. His research currently focuses on wireless sensor networks, IoT, and cyber physical systems with ultra-wideband communication and localization. The research performed in his group combines theoretical study and in-field validation and real-world applications, and has led to several awards. These include a most influential paper, Best Paper Awards at IPSN 3 times, PERCOM, EWSN, and IPIN. He is an associate editor for ACM Transaction on Sensor Networks and co-editor-in-chief of ACM Transactions on the Internet of Things. So as you can see, we're joined by a very august panel. And I guess the first kind of question that we're going to pose to each of our panelists are to ask, what are the grand challenges in networked sensor systems? And I'll first ask Nikki to come in.
Thank you very much, Andrew, and thank you very much for the kind invitation. It's an honor to be in this panel and I have the opportunity to talk about challenges in this area. So I think one of the most important challenges is the ability for networked sensor systems to perceive the world robustly. In spite of the vast diversity that we sort of face in the kind of situations where these network sensor systems could be placed, as well as the dynamic changes of the environment. So we can train sort of a machine learning model, for example, to make inferences from sensor data very nicely in a certain environment, and then we put it in the real world and we figure out that it doesn't work. How do we know that we are in this kind of different distribution scenario, how to quickly learn to adapt to a new context or to a new task? with very little or no additional training data. I think that's one important challenge. A second one I would say is the ability for sensor systems to basically have explainable and predictable failure modes. So basically know when their performance will degrade for any kind of reason, either because they happen to be in an environment that they don't know whether they can perform well, or they have intermittent communication or intermittent sort of power, or they just age as sensors and they need to be perhaps recalibrated or replaced. So it doesn't matter what, to be able to predict that failure mode in advance and to know what that failure mode looks like and give warnings about it. And then I would like to also mention a challenge of the fact that these sensors are networked and they are sort of collocated in a similar scenario. So they are smart collectives and they should behave as such. And so one big challenge is how to make them sort of efficiently extrovert agents, if you like. So know how to interact with the environment efficiently and learn from few interactions, but also with each other, when to share, what to share models, to share data, how to share in a privacy preserving way. And finally, what is starting, at least in our group, we're looking more and more closely into the idea of human sensor interaction. So anticipation of human intention, intuitive ways of controlling mobile sensors, ways of controlling what data they might want to share, intuitive storage and retrieval capabilities of high-level representations of sensor data, how to make sure that people who use sensor systems have at their fingerprints at the right place at the right time, the right kind of information from these network sensor systems.
Great, thank you, Nikki, for that brilliant outline and exposition. G, I'm gonna pose the same question to you. What do you think the grand challenges in network sensor systems are?
Thanks, Andrew. I think Nikki summarized many things very well. If I recall correctly, this is the 20th year of SenSys, right? And if I look back for the 20 years of this community, I think there's a consistent theme dealing with complexity. Complexity coming from, could be the number of nodes, could be the environment the nodes are in, could be the data that's collected by these nodes, and so on. I think that will continue to be our big challenge moving forward. The way we're dealing with the interaction between the digital world and the physical world has been at much more complex scales, and with our increasing capability of digitizing the physical world, that the challenge of understanding it, the challenge of interacting with it, and being serving like human and autonomous systems within it, that will continue to be the goal that why we design and implement and use these systems. And behind the scene, I think complexity will continue to increase. And that goes in the systems area. How do we connect all these nodes? How do we gather information and forming interesting network, efficient network with these nodes? But that's part of the story. I think more and more increasingly, we're paying attention to the complexity within the data. How do we understand it, right? The early years, I recall, where we're dealing with very simple sensors, temperatures and motions and things like that. Increasingly, we're dealing with complex sensors themselves, right? RF sensors and cameras and multi-modality and so on, but also different kinds of sensors sensing the same thing, the sensor fusion type of things. And we're involving more and more AI technologies and so forth to help us to turn data into cognition, right, into actionable meanings. And once we open that door, I think we are both embracing a lot of new technologies, and also we're getting closer and closer to application domains, right, where the verticals of these applications are quite different. I think at the beginning we can talk about system-wide. There's a couple of things that all systems probably share. And once we're dealing with data, it's very hard to say all kinds of data we're dealing with has like a very common theme. And I think that being application specific, being facing specific scenarios and the application requirements behind it, that will bring more and more complexity into the things that we're interested in.
Great, fantastic. I think you absolutely hit the nail on the head with this idea of evolving challenges that we're facing. Hey, what is your perspective on these grand challenges?
Well, I have to follow those two, huh? This is not going to be easy. Well, I think I'll start with I totally agree. I think the near-term challenge certainly is just, well, in the past we have all focused on getting that sensor data, right? And the community all came together and work on different layers of the system just to get that data. I think recently now we have the data, we're actually able to look at what that actually means. But of course, the challenge is really to get, like Jay and Nikki said, to get any kind of actionable cognitive things, reason out of it, right? We want to know something, not just the data. And I think the machine learning approach, just like they said, doesn't work. It's also not how people learn either. A baby doesn't need to touch a glowing hot stove 1,000,000 times before figuring out you shouldn't touch something glowing hot, right? So this is actually a unique opportunity for the sensor folks to actually incorporate all the environmental information, the cognitive information, maybe the physical model behind all these things in order to gain that understanding or the explainability aspect. So going forward a little bit beyond that, I think for the community as a whole, I recently moved to Michigan. One of the interesting thing about the process of moving is you get asked a lot of weird questions from people outside the field. One of the questions that kind of threw me for a loop was somebody asked, what is a standard algorithm in your field? I thought about it, well, we don't have a standard algorithm, and you gotta have a data set to have a standard algorithm. Wait a second, we don't even have a standard data set. Wait a second, we don't even have a standard application for that data set. It's like, wait a second, we don't even have a standard system for a standard application. So I think one of the things that we started off with one standard thing that everyone focused on getting that data. Then we branched out to all things under the stars. And now I think the next challenge may be actually to how do we come back together? Right now it's a little too diverse. I think the community can certainly maybe have a few, if we're a tent, perhaps we can, the next challenge may be to figure out some of the tent poles that the community can gather around.
Great, yeah, fantastic. Okay, Jim, Peter, what do you think? Do you think we need more pigs for our tent, or more pigs for our tent to hold it down, or?
I don't know. I think the question is challenging, but I was reflecting. I think I focused on the word network sensor system, and network is something that is kind of close to my heart. And I keep thinking that the challenges that we have ahead are less on the network sensing per se, but they are really at the intersection with the application, which is something that Nikki also touched upon. I mean, if we look back at what we've done for decades, right? We started with, we have sensors, we deliver the data to the sink as efficiently, as reliably as possible. Then machine learning came around, and then we started to do, cool things with this data. But maybe it's time to do the reverse, okay? So to try to push, not necessarily machine learning, but to push the application elements, the support for the application closer to the nodes themselves. Maybe it's a bit trite by now, but it's kind of the vision of Mark Weiser and so on, that computing should occur around us without us even seeing, not in the device in front of us, right? Right now it happens, relatively stupid or smart sensors, but then it works a lot in the cloud. So I guess the grand challenge maybe is to make the switch between networked sensors to networked intelligence. And here the work for the keyword for me here is network, not necessarily intelligence. And intelligence is not necessarily the connotation with machine learning or artificial intelligence, but it's the fact that we push down application elements into the network. And we've been doing this here and there. There are instances of this vision, but they're often application verticals. So can we do it in a principled way? Now that devices are becoming more and more powerful, there are even devices, again, to come back to machine learning, that are able to at least execute machine learning models. Maybe what we have in 5 years, 10 years, we don't know. But the point is, if we have all of this intelligence on the nodes, how do we network them? And this is not necessarily something that the machine learning community is going to solve, or they're going to solve their way. But we have 20 years of experience in making networks that are reliable, fast, scalable, right? Even, if you think about the recent development of concurrent transmissions and so on, they're super fast, super efficient. So how can we apply this to this switch to networked intelligence so that devices are decentralized, situated, autonomous, but do it in a way that is principled, so that as a community, we have a software fabric, a network fabric that is somewhat reusable towards this grand goal. And we don't just have silos of many different applications.
All right, so it seems every panelist answer to the previous question has mentioned machine learning in it. So that is leads to my next question. So what do you think the impact of machine learning / AI is and will be on those networked sensor systems? So I'm gonna start with Jian.
Oh.
Or you need a break?
No. Really? Actually, if the question is there an impact? The impact is evident, right? You just look at the program that we have in SenSys today, and you compare it with a few years ago, and as we go, there are many more. I think as I mentioned before, maybe if we push down intelligence, that's an element of the machine learning. What I see, however, is also that there is a sort of a limitation in the machine learning to some extent, in the sense that we see a lot of applications that are applying machine learning right, rather than contributing something new. It's like a new tool that we have is a tool that is very powerful, that is very versatile, but that often we solve a specific problem, we test it in a particular environment, we publish it, okay, and then it's really unclear then how you can go further with that or along that line. So I see it as a potential enabler for a number of things that we want to do, but we see it also severely biasing the goals of this specific community.
So you're saying we need to go deeper, not just applying existing models. Yeah, makes sense. So next I will go to Pei. I'm counting on you to be a little controversial.
Oh dear. I've been trying to be nice. You're tempting me. Well, I think machine learning's impact has always been there, even before machine learning was machine learning, right? I always feel machine learning has a good publicist. At the end of the day, it's a fancy regression. But you know, I think like it's a hammer. Like GP said, it's a tool that's nice and shiny right now. So everyone want to apply something. And I agree, you have to go deeper. And I really think that the stereotypical story I see is just machine learning folks coming to us and give us good data. And we know that's not possible. There's all these problems in the real world that limited by physics, that you cannot collect a lot of more data that they want or that we want. So so I think the impact initially after the shine wears off is really, how do we go deeper, right? How do we understand the world, not just collect data on the world and run some regression algorithms? How do we incorporate things we know around the world? What does that mean for the network? What does that mean for the computation? Yeah, so I hope that eventually most people will see that the shine wears off and see that, you know, it's just another tool that we need to use.
Jeff, please.
Although I'm the dean of AI Institute, I would say, especially out of research communities, AI has been overhyped by a lot. Right? Every time it became a buzzword, it was challenged by being overhyped. Especially when it applies to sensing data. I think we see a lot of success, right, in terms of image recognition, in terms of segmentation and natural language processing and so on. I call them media-based AI, right? Those are places you can collect a lot of media data, whether it's text or images or video and so on. People generate them. And when it comes to natural AI or things that's more of the physical world, things very easily fall apart, whether it's the quality of the input or the underlying sensing modality, which is hard to get labeled data, whether it's the data to collecting data, the sufficient amount of data itself to do any machine learning or AI on it. Right? Those are all very challenging when you deal with physical world and physical data. And a lot of things which were easy for human are really hard for computation, and vice versa. I think from the very beginning, people mix these two things up. They think if it's easy for people, it must be easy for machine. And we realized that, right? We heard a lot by it. Actually, the two AI winter earlier were very much caused by this type of overhype. But on the other hand, I would say machine learning as a tool, at the methodology, matches very well with our community, with network sensors. Things are being data driven, being like starting with thinking data first and how to collect them, how to mine meaningful information out of it. I think those are quite fundamental to what we're doing. So the marrying the two, or being very rigorous about what data means and how much you can get out of data with AI, with machine learning as the tool. I think that's the there's a lot of things to be hoped for, right, within that realm. So I would continue to think that the sensor network, our community need AI, need the new results from AI. But at the same time, we are defining a new category of AI, which are not very well addressed by the majority of the machine learning community. And I think we should amplify that. We should let people know that there are a class of applications and very meaningful, impactful applications that need the machine learning AI people to rethink the methodology and tools they have developed.
Thank you. So Nikki, what do you think? Do you think we need a new brand of AI for our community?
I think that's a really, really good point. And we are in a unique position to provide a completely different type of AI, if you like. To answer the original question, I'm very positive. I think the impact so far has been tremendous, but the impact has been primarily based on sort of training based on labeled data, so supervised type of learning. It doesn't fit, I think, the sort of way that data is collected in a sensor network or in a network sensor system. We have the advantage of having data being collected continuously, so huge volumes. We have the advantage that it comes from all sorts of different diverse conditions and it captures the changes in the environments. We should leverage that. So we should sort of look at, first of all, AI techniques that don't require labeled data, that just try to capture sort of the semantics and the structure of the world, so unsupervised, self-supervised methods. We should try to use techniques that work at the edge, of course, because we need devices to be semi-independent and also sort of deep learning algorithms to pick on the networked part of network sensor systems that sort of follow the distributed paradigm, what to share, what not to share, how to learn sort of collaboratively. So the network sensor systems, what is different is that huge amounts of data, great for machine learning, right? No labels, so we should sort of shift to different kind of learning, and also lots of the devices and sort of networked systems. So how do we learn collaboratively? And with these three sort of elements, we create an identity for machine learning in our field. Basically, which very much supports what Ji was saying before.
Thank you.
Great. Okay. Yeah, I think you set out between you all like a really strong outline of AI, and I think especially the comments of what happens when the shiny wears off, I think are really valid to say what we as a community need to treat AI as perhaps not as a tool that comes externally, but as a tool that we also need to take a hand in driving forward. Moving on to kind of our next kind of area, I think we ask, what's stopping us? What are our key bottlenecks or limitations that are hindering progress? I'm going to start with Pei this time. So Pei, what's stopping us?
Well, I think what's stopping us is that if we get something working, it works for one application. It works, and there's no comparison. If you look at the papers in this community, there's a lot of great papers. But every year you see something, whatever area I'm in, right? I think every year I see a paper that says deployment is hard. and it's a completely different deployment. And every year, you see some great papers that say, oh, I wonder how this compared to the previous year's paper. And you can't, because we don't have that, I guess, killer app, if you will, or we don't have the data that's being shared so we can compare against each other's, or the algorithm that's even shared. And even if it's shared, it's going to be almost impossible to use. So I see that maybe our limitation, not in the fact that we're not creating new things, new and awesome things, but merely because the outside world, outside this community, can't really take it and digest it and really understand how that impacts them. So that's my worry, or couldn't figure out how to do.
Great. Yeah. Indeed, like maybe we need MinNIST for sensor networks to solve all our problems. Jan?
Sure. I mean, I was about to say that's another problem, benchmarking. I mean, we did a lot of what we did because at least we had common test beds, for instance, right? So, and the leap from just simulations and so on to really testing on widely accepted and shared public test beds was a big leap. But then the lack of benchmarks is also, I mean, it's a limitation, but it's also a sign of richness. I mean, in the sense that in this community, there are not just sensor networks. Actually, if you look at the papers, there are very few that are left in the program, which, yeah, is a pity, at least in my opinion. So it's also difficult to some extent to have a benchmark, right? Maybe because we are not so focused as some other communities that like Vision and so on, that have a very simply stated type of benchmark. Okay, that's one thing. Another thing, maybe this goes back to the challenges, is also getting rid of batteries. Okay, and for everything that is low power, wireless, and so on, batteries, or at least the limitations that are induced on batteries, is still perceived as something limiting. Okay, when you approach, and I don't know what's your experience, but I also feel that we're not being particularly good at communicating what we have with industry, which is not necessarily, the industry's fault, okay? But it's possibly our fault. I don't know. If you think about all the papers and all of what we've done for wireless sensor networks and so on, applied to control, monitoring, and so on, but at least my experience talking to big industries is that they're very reluctant still, many of them, in using wireless massively because it's still perceived as unreliable. It's still perceived as, as I said, battery powered. So there is this gap, and if you look instead at what's been published at Senses, the WSN dependability competition, and so on the contrary, we've been developing protocols that are basically achieving 5 nines, even under massive interference and so on. So I think, and the fact that at Senses there is not a strong industry presence, I think that's also a downside on our side. As I said, it's not necessarily that they are the bad guys. I mean, also, if you look at some of the standards, look at Bluetooth 5 and the mesh, right? It's ear light of distance from what has been done in this community. Yet, there is some provision for security or interoperability that is something that we tend to, not consider, but it's also what matters. So I think we need to keep an eye on the progress in general, and not just the progress of our field, and to find ways to do a better discourse or a better marketing of our research towards industry.
Great, thanks, JP. Nikki, do you feel that it's industry that's going to perhaps resolve some of these bottlenecks, or that they are part of this things that are stopping us from really moving the field forward? I am muted.
I think working with industry is a really good thing, and it's also a very time-consuming thing for, say, researchers who are trying to do a PhD or a master's or a postdoc. But there are huge sort of lessons to be learned from practical issues that industry sort of follows. Industry may have much higher standards in terms of sort of robustness. And the point about trusting sort of sensor systems is a very, very important one that often people are reluctant because they know, a sensor system could work for a certain period of time and then degrade afterwards and not be reliable enough afterwards. And then to make it reliable enough and to make it work for sort of real world application, one has to invest quite a big amount of sort of engineering effort. And this is not always appreciated when it comes to reviewing papers and so on. Also, if you want to see how a network actually performs over longitudinal studies, like if you leave it, again, this is something that we don't have the luxury of time to do when doing research, and sort of especially for students that have a very limited sort of amount of time. So these are kind of inhibitors. Other one could be for applications like healthcare, where you need to involve people. And again, these timelines are quite long because you need to get approval, ethics, you need to get the people to participate in experiments, you need to pre-process, post-process data to protect privacy. So there is like a lot of sort of steps you have to go through. So these are all kind of, one can think of them as bottlenecks, but at the same time, it's also what gives the unique flavor to our systems sort of based research, and what differentiates us from sort of people doing pure machine learning. So I think that benchmarks, if we become better at doing benchmarks or building benchmarks of benchmarks. So for example, say, one university sets up a benchmark and you've got algorithms working there, and you want these algorithms to also work without training or without very much modification to a new benchmark. And this is like the next step of sort of standards that we put for our algorithms, that they are sort of not as tightly coupled to either the deployment or the benchmark where they are tested. They are easy to sort of mold and adapt and use somewhere else. This, I think, would sort of spread the progress of our research much, much faster, and to much more industrial sort of partners and other applications.
Great, thanks. G, do you think as well? What do you think is stopping us? Where are our major bottlenecks?
Yeah, it's hard to believe we're 40 minutes into this panel, but nobody has mentioned metaverse. I'm not joking. I think metaverse to me represents three things. It represents a killer app that at least draw a lot of imagination and draw people together, and people want to use it. It represents a platform that people can innovate on top of it. Make innovation easy. I think that's how you draw people into a field. It also represents a network effect, which is related to platform, that when people contribute to it, the result got accumulated, and you got this n squared or exponential value out of these networked effects. And most of the very successful things have that nature, right? You can say metaverse is a hype right now, right? It could go away, but at least having those for a period of time allows investments to go in, allows intellectual capabilities to go in, allows things to accumulate, and what's left over could actually apply to different other things, and that's what you leave for a legacy, right? The thing could fail, but the legacy will live on. unfortunately, I think we had the opportunity in the maybe early 2000s and time like that, right? Sensor network was a buzz. A lot of people from very different fields jump into sensor networks and share the vision. However, I think maybe it's the nature of our field, right? We didn't come up with a killer app. We didn't come up with a dominating platform. And things become quite fractured, right? We have very scattered applications and platforms, and maybe it's in fact, I think it's part of nature of it, right? Because we are dealing with very constrained systems, whether it's energy constraints, whether it's computational platform, whether it's networking, whether it's the size and weight and all that, which makes you want to squeeze out of the last bits of value out of the platform you have, and end up with everything's custom design, and that builds the bar very high, and make innovation, common innovation or network effect, very hard to achieve. And I think moving forward, actually, I see a lot of these mobile sensing come out of the sensing community like us. But being on a very common platform that everybody can use and adopt, and there's a lot of investment going into it. Those technologies, right? The mobile sensing type of technology got adopted much more wider than some other things that equally cool came out of the research field. And I think moving forward, I'm looking forward to things like that, right? Things like AR, VR, metaverse. I'm imagining it not just for a joke. I think there is a trend that computation and information and people interaction are coming together that make that type of interactions achievable. And I would hope that some of the technologies that we build in here will be either within it or being the main player in it, and or we'll come up with something even cooler than that. That will be a big step, a big leap that can move forward field.
All right, so all of us are educators and supervisors. So my next question is, what advice would you give to new students embarking in this field? So I'm gonna start with Jen.
I guess learn machine learning, because one way or the other, you'll have to either compete or use it. So that's one. The other is, I guess, I'm not sure if it's really specific. I think it's because this field is so dominated also by applications, be them real world deployments like over sensor networks, which were a way to validate your protocols and so on, or more recently, the many applications that we see with where there's a problem and machine learning is thrown at that problem for the application. I think the advice is be careful, or at least be aware of the fine line between application and innovation. Because you need them both in theory, right? You need the innovation on the research side, and you need at least some reference application or some form of validation that it works in the real world. Be careful not to err too much on the other side and be totally hijacked by the application. So it's difficult, but that's the kind of balance that probably one should keep in mind in general, and in particular when doing a PhD. And then, of course, question your advisor always, and that holds for any topic, I would say.
Yeah, that's excellent advice. Application change, but fundamentals do not, right? So I would like to ask Jay the same question. Jay, you have a very, like you had a lot of experience, first working in industry and now move to university. So can you share us some advice for students?
Yeah, it was not until recently after I became a educator and started to take undergrad students and try to move them forward, that I realized how hard our field is. And people who are good in our field have to learn from all the way from, hardware devices to embedded software to signal processing to data and application all the way through. It's very hard to get all that into the education system. Actually, I was part of redesigning our course system for AIoT, right? The area of AI and IoT intersect, and just an amount of things we have to squeeze into it. It's just, you can't take it with the undergrad and education. And we end up throwing a lot of, which I would imagine part of engineering education to begin with. For example, we have to squeeze all the circuit and systems and analog and everything into one class, and all the digital and computer architecture and all those things into one class. Things it took me maybe a few years to learn when I was a undergrad student. They have to learn it in a semester. That's hard, right? I think that actually prevent a lot of very good students to come into our field just by looking at how much we have to teach them, and then they have to learn to even get started with good research and good system engineering. I don't have a very good solution. I have to go back to the platform view, right? If we have elevated enough that people can only need to, I look at some of the quote unquote normal AI student, right? They don't have to understand where data come from. They don't have to understand how computer works at all, right? It's just Python, and there's a data set in Python, and it's all sort of piecing together different kind of libraries. It's very different in our field, and I think as a community we have to come up with several very good platform abstractions, so we can teach students on top of those, so we can sort of separate the concerns. Otherwise, everybody has to learn everything to do good work. So that's my feeling. I don't have a very good solution, but that's the challenge I'm facing.
Thank you. So Nikki, any advice, like what research topic to pick for new students?
I think I'd like to be a little bit more controversial and give a kind of different light to what G said, and say, if there's so much to learn, or you can learn, why don't you just pick what you enjoy the most? You can see it in a different way. You can see that there's space for innovation in so many different types of contributions. So you can work on novel sensor modalities, you can work on sort of inference and learning, you can work on, I don't know, optimization across software and hardware, you can work on building test beds and simulators and benchmarks and benefit the whole community. I would say what fits you best, like what is the most sort of greatest interest, and pick that sort of area that you like. And then let some other members of the team worry about the other parts. So this is like a supervisor kind of responsibility to see whether you can build a team where different people sort of fill different gaps. And then, but figure out what the problem you're solving is, because often I find that we very much are eager to jump to solutions, and then we try to figure out what the problem is, how to motivate that paper. So think of the problem and think of the impact it's not early enough to think about it. Even the first day you land at your sort of university and start studying, pick what you like and figure out why you're doing it, in other words. But also it's good to have some idea of all the other parts. As G said, it is a complex system, and you need to have some knowledge of the other parts, but not perfect, perhaps.
Absolutely agree. So Pei, you have the last word for this question.
Well, I'm not going to be controversial because I totally agree with everyone. When students usually ask me this question, I tell them to run away. And the good ones always ignore that advice. So I found that to be a good filter. I think one thing that students don't recognize is that it is actually the wide range of knowledge that we do need. It is that, of course, they're going to have some part that they enjoy, and they're going to focus on that part. But even if you do, we do need to understand something about the hardware, something about the middleware, something about the machine learning, something about going all the way, I think, something about how to comfort the patient when they accidentally defecate on your sensors. Or like Shijia, I think she's one of these pixels on the video here, crawling under a pig pen, installing the sensors while avoiding the defecating pigs above her. I think I see an unfortunate trend with our research. Or like working with the military, refueling a B-1 bomber, like how to make the soldiers happy, right? So I think that's part of the excitement of being so wide type of applications. You get to work and learn on things that's so different. And I know we've been bad-mouthing, including myself, been bad-mouthing all this diversity in the field, but that's actually what makes it fun. But that's also kind of where I often surprise students that, what do you mean I have to fill out an IRB form to work with babies? So it's, I think, both a blessing and a curse, but certainly a lot of fun.
Okay, so thanks for answering all the questions. And at this stage, we're going to open up the floor to invite a question from the audience. We start from the local audience, and I notice we do have one question from Slack channel. Anyone?
Hi, Sriram from National University of Singapore. I had a question along a slightly different tangent, a more sort of security-oriented tangent, I guess, which is, we talk a lot about scaling sensor networks and then, making them larger, making them more complex, getting more data. But there's also like another sort of pool of research now that works on exploiting that large amount of data. So, for example, using accelerometers or just like one to, eavesdrop, for example, or all kinds of things where we exploit existing sensor data to, have security or expose privacy vulnerabilities. So this feels like an arms race where we install more sensors and then we find more issues and then we just keep going back and forth. So I wonder whether the panel has any opinions on how we can either avoid this arms race or solve it, or I work in this field as well. So I'm also concerned, even with a simple sensor, we find privacy issues, just by extracting a few bits here and there. So I guess my question is, how do we approach this issue of sensing and oversensing and security as we expand these networks? Yeah.
Great, thanks for the question. Anyone from the panel want to address how do we balance these trade-offs, or should I just give it to a random?
I could get it started. I think there's no avoiding this. If before you know you can sense it, how do you know that there's a privacy issue, right? So I think it's natural. I think there's an old Chinese saying that the thief, if the good guys go up 1 feet, the bad guys go up 3 or something like that. I mean, it's been like that since the era of physical locks. I think why would it be any different now?
I would turn around and say privacy first, right? We enjoy too much of, in some sense, unethical things just being ignored. We ignored a lot of those, which should be a real concern. We should not do human sensing before thinking about privacy issues, right? I mean, we should not consider some of these applications without first thinking about the privacy concerns and so forth. I think we lack in our education and in many times the mindset, whether this should be done or how this should be done. We always think privacy as sort of the patch after we've done it and say, oh, maybe we have this concern, let's do something about it, or write a disclaimer to avoid it and things like that. But those are not the right way, in many cases, not the right way to do it. So I think privacy should be at the frontier in many things that we consider, and we should educate all students about it.
Yeah, I totally agree, and I think that there is there are very interesting research problems that could come out of trying to protect the privacy, both in terms of sort of highlighting a privacy issue in itself could be a research problem. I remember a few years ago in the lab, we were showing how with acceleration data from a smartwatch, you're able to infer, say, the PIN that people use to unlock it, or that swipe, the code that they swipe. And like the first thing that we did is just sort of show that this is like a privacy concern, or this is a security sort of concern. But then you then can think one step further and say, okay, how do you then sort of collect and store the data in a way that this risk can be mitigated or can be avoided? So in a way, you have like a range of first research problem, second, third, in terms of discovering the problem to begin with, and then thinking about mitigation sort of mechanisms. And I totally agree with G that we have to think of these things in advance and at the design level, but also that it's often impossible to think of everything at the design level, and there are things that will come up later on. And let other people as well sort of shed light into any privacy sort of implications of systems we have built, and feel very comfortable with each other, sort of working on each other's systems and discovering vulnerabilities of that type and sorting them out. So I think we should look at it collaboratively and think of it as a good thing for research and good thing for people, sort of data protection.
I think, unfortunately, I can hear only half of what is said from this position, but so maybe I'm repeating. I think it's also a function of where you position yourself, right? Privacy is very important, but for some applications or for some fields. If you are into monitoring control, for instance, in industrial IoT, in situations where your network is inherently secure, then security, maybe it's not even an issue, right? And so again, it also depends on how you position yourself in terms of the researchers. If you are very close to the application, you're selling that as a, almost a done solution, then maybe security is more of an issue when compared to situations in which you are designing a new communication media, a new communication protocol and stuff like that. Of course, the book says that, you shouldn't have security afterwards, but there is also, and then the other side of the coin, that you cannot stifle progress or research or, looking into new solutions because you don't have a security solution at the moment. So I think there is something to be said for investigation at large, for innovation at large, regardless of security. I mean, maybe from that, if you are able to show that there is enough incentive, then things can be maybe morphed into something that is more secure down the road, or it maybe inspire solutions that are more secure. But it's still, I mean, we are researchers, right? So we're still part of the, discovering new things. So security is important, but I feel sometimes it's perceived also or used to say, well, this doesn't work because it's not secure.
So there's I'm going to ask on behalf of Anurada Ravi from Slack. The question is, what will be the focus in future? Is it going to be algorithmic or software techniques to incorporate the cognitive environment to understand the data and respond to real-time situations better? Or will it be new hardware sensors coming up in the market with different sensing capability, innovatively exploiting the nature of physics? So like if you're given those two options, so what would you say that's going to be the focus of the community?
Yes. Both.
Exactly. I was about to say the same. It doesn't seem an or. It seems we would need an and, right? We need the software fabric and the network fabric to design these new systems. But of course, we need also hardware innovation. And as I said, a batteryless sensor that is actually has decent range and decent computation capabilities wouldn't hurt. So I think we need both. Whether we're going to have it and in what form remains to be seen.
So if I have to take a stand, I think the question is about, right, if you're forced to give an answer, I think the disruption of having a new type of hardware is bigger than the disruption of software technologies. One of them, to me, is a sort of a continuous progress that things build gradually on top of each other. That's typical for software, right? We're not inventing dramatically a new software technology. But on the other hand, hardware can come in and drastically change some of the assumptions or some of the ways that we interact with the physical world. So yeah, if I have to hope, right, something comes up, I would put my bet on a new type of sensing capabilities. If something can sense dark matter, right, I think we're all for it.
And another angle might be to say whether we can use software to get better sort of hardware, combine, say, novel sensor technologies, I don't know, nanomaterials, smart materials, but also how we use them, how we combine them, how we design them. I think software could help a lot in the design process to sort of come up with very, very efficient machinery and very, very efficient sort of computation and sensing modules so I can also see like something that links the two that could bring sort of a new way of doing things in our community.
I guess we are more or less in agreement. So with that, that actually concludes the panel discussion. Once again, I'd like to thank all the panelists, especially Jane, it's very late in your time zone, and thanks for the other audience and also both local and online for participating.
All right, thank you.
Thank you.
Thank you for inviting us. Thank you. Thank you.